Hello there, welcome to the Science Owl Station channel. Today we are going to do something a little unusual. We are going to speak of darkness, not the ordinary darkness that falls when you close your eyelids or when the sun dips below the horizon, but a darkness so complete, so absolute, that it does not merely absorb light. It swallows the very idea of light. We are going to speak of black holes. Before you settle deeper into your pillow, before your breath finds its own slower rhythm, I would like to know where this voice is finding you tonight. Perhaps you are lying in a bed near a window, and the moonlight is tracing silver lines across your blanket. Perhaps you are on a sofa, the house finally quiet, the last cup of tea grown cold on the nightstand. Perhaps you are in a city where the streetlights never sleep, or in a countryside so still you can hear the turning of the earth itself. Wherever you are, whatever time the clock shows, pause here for a moment and leave a word. A city, a country, a feeling. Let this small act anchor you to this moment, to this shared stillness, before we journey together into the deep. Wherever you are, let the world slow down for a while. Soften your gaze, let the hum of life around you fade, and gently drift with us into tonight's quiet exploration. Imagine, if you will, a place where gravity is no longer a gentle hand that pulls apples from branches or keeps the moon tethered to its patient orbit. Imagine gravity as something else entirely. A force so immense, so ravenous, that it bends the fabric of the universe into a well so deep nothing, not even a whisper of light, can climb back out. This is the black hole. And yet, despite its name, it is not truly a hole. Not in the way we imagine a cave in the mountainside or a tunnel carved through rock. A black hole is instead a region of space-time where gravity has reached its final, absolute victory. To understand this, we must first remember that space is not empty. It is not a void. It is a living, breathing tapestry, a fabric woven from 3 dimensions of space and 1 dimension of time, all stitched together into what physicists call space-time. This fabric can stretch, it can ripple, it can curve. And when you place something heavy upon it, a star, a planet, even you, the fabric bends slightly inward. That bending is what we feel as gravity. The heavier the object, the deeper the curve. A black hole is the place where the curve becomes infinitely deep. It is not a mouth that swallows. It is a wound in the very substance of reality. Why do we call it black? Because light, the fastest thing in the universe, the thing that travels 980,000 times faster than the speed of sound, cannot escape it. Light has no mass, and yet it follows the curves of space-time obediently, like a river following the slope of a valley. When the valley becomes a vertical cliff, when the slope becomes a bottomless pit, the light cannot turn back. Simply falls, and so the region emits nothing. It radiates no warmth, no color, no signal. It is the absence of information. It is the closest thing to true nothingness the universe has ever fashioned. But here is the quiet astonishment, the thought that settles into the mind like sediment in still water. We know with near certainty that black holes exist. They are not theoretical phantoms. We have seen their shadows. We have heard their mergers, translated into sound, the final chirp of 2 singularities spiraling into one another across 50 million light-years. We have watched stars orbit empty patches of sky, tracing invisible ellipses around something that emits no light but tugs at them with the insistence of a tidal current. And yet, for all our certainty, a black hole remains one of the most tender, unsettling mysteries the cosmos has ever offered us. In the early 20th century, a man named Karl Schwarzschild was serving on the front lines of the First World War. Between calculating artillery trajectories for the German army, he found time to solve Einstein's equations of general relativity. What he discovered, in the cold of the Russian winter, was a mathematical description of a point of infinite density, a singularity wrapped in an invisible boundary. He did not set out to find a monster. He was simply following the logic of gravity. And the logic told him that if you compress enough mass into a small enough sphere, the fabric of space-time collapses. It does not tear, not exactly. It simply folds in on itself, creating a region from which nothing can return. That boundary, that point of no return, is what we now call the event horizon. It is not a physical surface. You cannot touch it, cannot stand upon it. It is a mathematical threshold, a place where the escape velocity, the speed needed to break free from gravity's grip, exceeds the speed of light. Once you cross it, there is no back. There is no reverse gear in the machinery of space-time. The horizon is not a wall. It is a one-way door. And so the black hole sits in the darkness, silent, patient, gathering nothing and everything. It does not actively pull. It does not hunt. It simply waits, curving the space around it, bending the path of any stray star or wandering cloud of gas that ventures too close. Its appetite is not a matter of will. It is a matter of geometry. It is the steepest slope in the universe, and everything that passes its edge slides inevitably toward the bottom. But here, before we descend further, let us pause. Let us linger at the threshold, not yet crossing. Because the event horizon is not merely a physical boundary. It is also a boundary of knowledge. Outside it, we can observe, we can measure, we can infer. Inside it, the laws of physics as we understand them cease to speak. The silence that follows is not the silence of ignorance. It is the silence of a language we have not yet learned. So tonight, we will approach the edge with reverence. We will speak of giants and relics, of dying stars and ancient echoes of the Big Bang. We will follow the path of light that never returns, and we will wonder gently about what lies at the bottom of the cosmic well. Not because we seek fear, but because wonder itself is a form of rest. To gaze into the abyss and not flinch, that is not courage. That is trust. Trust that the universe, even in its most extreme gestures, is still beautiful. And so we begin. Before there was darkness, there was light. Before the event horizon drew its invisible circle in the fabric of space. Before the singularity curled in upon itself like a seed waiting for an eternity that would never arrive, there was a star. And stars, for all their fierce and brilliant lives, are not eternal. They are born in nebulae, those vast, slow-swirling nurseries of gas and dust, and they spend millions or billions of years in a state of delicate balance, a quiet war between two titans, the inward crush of gravity and the outward push of nuclear fire. For most of a star's life, this war is a stalemate, but every war eventually ends. To understand how a black hole is born, we must first understand what a star truly is. It is not merely a ball of burning gas, though that is how it appears to our distant eyes. A star is an act of compression. Gravity pulls every atom toward the center, squeezing the core with a pressure so immense that hydrogen atoms, stripped of their pretense, fuse into helium. This fusion releases energy, photons that struggle for thousands of years to climb from the core to the surface, finally escaping as sunlight, starlight, the glow that reaches us across unimaginable distances. That light is the star's shield. It pushes outward against gravity's pull, holding the star open, keeping it from collapsing under its own weight. But fusion does not last forever. Hydrogen, the fuel of youth, is finite. When the core has converted enough hydrogen into helium, the star begins to change. For a star like our Sun, this change is gentle. It swells into a red giant, sheds its outer layers in a luminous shroud, and retreats into a white dwarf, a dense, fading ember no larger than Earth, held open not by fusion but by the quiet resistance of electrons packed so tightly they can be compressed no further. This is a peaceful end. But for a star much more massive than the Sun, peace is not an option. When a massive star 8, 10, 20 times the mass of our Sun exhausts its hydrogen, it does not simply dim. It begins to fuse heavier elements, building layers like an onion. Hydrogen at the surface, then helium, carbon, neon, oxygen, silicon. Each stage burns hotter, faster, more desperately. The core becomes a forge of iron, and iron is the threshold. Fusing iron does not release energy. It consumes it. In that moment, the outward fire falters. Gravity, patient and relentless, seizes its opportunity. The core collapses. In less than a second, a sphere of iron the size of Earth is crushed into a ball no larger than a city. The layers above fall inward at nearly a quarter of the speed of light, then rebound off the impossibly dense core and detonate outward in a cataclysm we call a supernova. For a few weeks, that single star outshines an entire galaxy. It scatters the elements of life: carbon, oxygen, calcium, iron, across the void, seeding future worlds, future bones, future eyes that will one day look up at the night sky and wonder. And at the center of this violence, something remains. If the core's mass is below a certain threshold, it becomes a neutron star, a city-sized sphere of pure nuclear matter, so dense that a teaspoon of its substance would weigh 1 billion tons. But if the core is heavy enough, if gravity's victory is absolute, even the resistance of neutrons is not enough. The collapse continues. The star vanishes into itself. A black hole is born. This is the most common origin, the lineage of giants. But it is not the only way darkness enters the universe. In the first moments after the Big Bang, the cosmos was not the cold, sparse expanse we know today. It was a roiling, unimaginably dense sea of energy and matter, a place where the very concept of temperature had not yet cooled into meaning. In that primordial chaos, some regions may have been denser than others, slightly denser, and if a region was dense enough, it could have collapsed directly into a black hole, bypassing the slow drama of stellar evolution entirely. These are the primordial black holes, ghosts of the infant universe, born not from dying stars but from the birth pangs of reality itself. Some may be as small as a mountain, compressed into the volume of a single atom. Others may be scattered through the dark matter that weaves between galaxies. We have not yet found them, but we have not yet stopped looking. And then there is a third path, quieter than a supernova, slower but no less profound. Far from the light of any star, in the cold solitude of deep space, two dead stars can find each other. Neutron stars, the cinders of ancient supernovae, orbit one another in a slow gravitational waltz, each revolution drawing them infinitesimally closer. They radiate their orbital energy away as ripples in space-time, gravitational waves, and as they lose energy, they spiral inward. For millions of years, they circle, and then, in a final, violent instant, they touch. Their surfaces merge, their masses combine, and if the combined weight crosses that invisible threshold, the same threshold Schwarzschild wrote down in his field equations a century ago, a new black hole opens its event horizon to the darkness. So you see, a black hole is not a single thing. It is a fate, a destination, a final state that matter can arrive at by many roads. It is the resting place of giants, the relic of the universe's first breath, the quiet aftermath of a long celestial embrace. And each of these origins leaves a trace. Each black hole carries, imprinted in its mass and spin, a memory of how it came to be. When we detect the chirp of two black holes merging, as we did for the first time in 2015, we are not merely hearing a collision. We are hearing an inheritance, the echo of massive stars that lived and died billions of years ago, in galaxies that no longer exist, their cores collapsing and waiting through cosmic time until at last they found each other in the dark. And in that final spiral, they released a pulse of gravitational energy 50 times greater than all the stars in the observable universe combined. And then silence. Then the ring down of a single larger black hole, settling into its new shape, its new stillness. It is easy to think of black holes as endings, and in a sense they are. They are the final page of a star's story, the last sentence written in light. But endings, as we know, are also beginnings. The elements scattered by the supernova that birthed a black hole will one day form new stars, new planets, new life. The gravitational waves from a merger carry information across billions of light years, arriving at our instruments as a signal no louder than the rustle of leaves, decoded by human hands and human curiosity. The black hole itself, silent and patient, waits, not as a destroyer, but as a presence, a question we have only begun to ask. So rest now if you can. The stars above you, even the ones that seem eternal, are following their own paths toward distant futures. Some will fade, some will burn out, some will leave behind these quiet shadows, these wells in the fabric of space-time. And we, here on this small planet, are the universe's way of knowing itself, of telling its own story, slowly, gently, one discovery at a time. If you were to gather every black hole the universe has ever made and arrange them not by name, not by discovery date, not by the constellation in which they happen to reside, but simply by size, by the gentle curve of their mass, you would notice something peculiar. They do not form a smooth line. They cluster, like islands in a vast ocean, separated by gaps that speak not of what is missing but of what is possible. And so we give them names, these families of darkness, not to cage them but to recognize them, to understand that a black hole is not one thing but many. Let us begin with the most intimate, the closest to our own scale, though the word close here is deceptive. Stellar mass black holes are the children of dying giants, the remnants of stars that began life with at least 8 times the mass of our sun and ended it in the violent exhalation of a supernova. Their masses range from about 3 to several tens of solar masses, 3 to 50 suns, compressed into a sphere no larger than a city. 3 suns, crushed into a width you could drive across in an afternoon. It is a density that defies the imagination, and yet it is the most common black hole in the universe. We believe there are 100 million of them scattered through the Milky Way alone, each one a silent monument to a star that no longer shines. But they are not easy to find. A black hole of 10 solar masses, quietly adrift in the darkness, emits nothing. It does not glow, does not reflect, does not announce itself. We only detect it when it is not alone, when it has a companion star, a partner in some cosmic dance, and when it draws gas from that companion into its waiting mouth. That gas does not fall straight in. It spirals, slowly, patiently, heating as it circles, until it glows white-hot and sings in X-rays. And in that glow, we see the invisible. We measure the orbit, calculate the unseen mass, and we know something is there, something heavy, something dark. This is how we found Cygnus X1, the first black hole ever confirmed, back in the 1960s and 70s. It was a binary system, a blue supergiant star locked in embrace with an invisible companion of about 21 solar masses. The X-rays told us where to look. The orbit told us the weight. And the weight told us that this could be no neutron star. Neutron stars have a limit, a maximum mass beyond which even their dense nuclear matter cannot resist gravity. Cygnus X1 was beyond that limit. It was, by any reasonable definition, a black hole. But stellar mass black holes are not the only inhabitants of this cosmic archipelago. There are others so much larger that they belong to a different order of magnitude entirely. These are the supermassive black holes, and they sit at the centers of galaxies like spiders in vast, slow webs. Their masses are not tens but millions, even billions of times the mass of our sun Sagittarius A*. The black hole at the heart of the Milky Way weighs about 4 million suns. The one in M87, made famous by the first direct image of a black hole shadow, weighs 6.5 billion. And these objects are not merely larger versions of their stellar cousins. They are something else entirely. How do they grow so large? This is one of the great questions of modern astrophysics, and we do not yet have a complete answer. We know that they cannot be the remnants of single stars. No star is massive enough to leave behind a billion solar mass black hole. Instead, supermassive black holes must grow over cosmic time, swallowing stars, merging with other black holes, drinking from the slow river of gas that flows into galactic centers. But even this seems insufficient. Some of these giants were already in place when the universe was less than 1 billion years old. Far too soon for such patient accretion to work. Perhaps they were born large from the direct collapse of primordial gas clouds in the early universe. Perhaps they grew through rapid, repeated mergers. Perhaps there is a mechanism we have not yet imagined. Between these two families lies a curious middle ground, intermediate mass black holes. For decades, they were theoretical ghosts, objects we suspected existed but could not quite catch. They would fill the gap between stellar mass and supermassive, from a few hundred to a few 100,000 solar masses. But the evidence was elusive. Then, in 2019, something remarkable happened. The Laser Interferometer Gravitational Wave Observatory, LIGO, in its quiet, patient listening, detected a signal from a merger unlike any before. One of the objects weighed about 85 solar masses, the other about 66. Their union produced a black hole of roughly 150 solar masses. This was not a stellar remnant. This was something else. An intermediate mass black hole, born in the instant of its parent's collision, and carrying in its spin the memory of that violent embrace. And then there are the smallest of them all, the black holes that may not even exist but remain stubbornly in the equations. Primordial black holes, sometimes called miniature black holes, are relics of the Big Bang. In the first fractions of a second after the universe began, density fluctuations could have collapsed directly into black holes, bypassing the need for stars entirely. These objects could be as light as a mountain compressed into the volume of a single atom, or as heavy as a planet, quietly passing through the solar system without anyone noticing. We have not yet found them, but theorists have not yet ruled them out. And so they remain, a quiet possibility, a memory of the universe's first breath. What is remarkable, what settles into the mind with a kind of slow wonder, is that these different families of black holes speak to different epochs, different processes, different scales of cosmic time. A stellar mass black hole remembers the death of a single star, a life lived in the usual way. A supermassive black hole remembers the growth of a galaxy, the slow accretion of 10 billion years. An intermediate black hole remembers a collision, a moment of union in the darkness. And a primordial black hole, if it exists, remembers the universe itself, remembers a time before stars, before galaxies, before light. Each is a record, each is a story, and we, from our small planet, are learning to read them. So when you look up at the night sky, know that the darkness between stars is not empty. It is filled with these silent witnesses, these remnants and relics, these questions waiting to be asked. Some are nearby, drifting through the spiral arms of our galaxy, invisible companions to distant suns. Some are at the centers of galaxies billions of light years away, their event horizons casting shadows across the radio maps of patient telescopes. And some, perhaps, are passing through the space between us and the moon, smaller than a grain of sand, carrying with them the signature of the universe's first instant. We do not know them all. We have not found them all. But we are listening, watching, waiting, and the darkness, for all its silence, is slowly beginning to speak. There is a moment just before dawn, when the sky is neither dark nor light but something in between. A deep blue, almost violet, that holds its breath in anticipation. The stars have not yet faded, but the eastern horizon begins to glow with a soft, diffuse radiance, the promise of a sun still hidden below the curve of the earth. In that suspended moment, the world is all threshold. You are neither in night nor in day. You are at the edge. A black hole has its own thresholds, its own edges. And like that moment before dawn, they are not walls but boundaries, places where one state of being gives way to another. To understand a black hole, we must learn to see these edges not as lines on a map but as landscapes. For though the interior of a black hole is forever hidden from us, its exterior is radiant, dynamic, alive with motion and light. The darkness at the center is surrounded by a corona of visibility. And it is here, at the boundary between seen and unseen, that we begin. The most famous of these edges is the event horizon. It is not a surface in any ordinary sense. You could not stand on it, could not touch it, could not mark it with a flag. It is, instead, a mathematical membrane, a place in space-time where the escape velocity equals the speed of light. Inside this radius, the pull of gravity is so immense that to escape would require traveling faster than light itself. And since light travels at the universe's ultimate speed limit, Nothing inside can ever cross back out. The event horizon is the point of no return, the threshold beyond which all paths lead inward. But here is the strange, tender paradox. If you were to fall toward a black hole, you would not feel the event horizon at all. You would not see a dark wall rising before you. You would not sense a sudden jolt or a change in the texture of space. The horizon is invisible to the one who crosses it. From your perspective, falling freely, you would simply continue drifting downward, the stars still visible above you, the darkness below you growing no darker. Only much later, as you approached the singularity, would you feel the tidal forces begin to pull. But the horizon itself, it passes without ceremony, without warning, without even a whisper. You would not know when you became unreachable. To an observer watching from a safe distance, however, the story is entirely different. They would never see you cross the horizon. They would see you approach it, slower and slower, your image reddening and dimming as the light you emitted struggled to climb out of the deepening gravity well. They would see you frozen at the edge, forever approaching but never arriving, your final moments stretched into infinity. This is not an optical illusion. It is the signature of extreme gravity, the way space-time itself slows near the horizon. For the distant observer, you are suspended at the threshold for all eternity. For you, the fall continues. Just outside the event horizon lies another boundary, not of inescapability but of light itself. This is the photon sphere. Here, gravity is so strong that light no longer travels in straight lines. It curves, bends, orbits. At precisely the right radius, photons can circle the black hole indefinitely, trapped in an unstable gravitational embrace. If you could stand in the photon sphere and look sideways, you would see the back of your own head, light having traveled all the way around the black hole to reach your eyes. The photon sphere is the place where light forgets how to leave. It schemes the edge of the abyss, circling like a moth around a flame, never falling in, never escaping, forever in motion and forever captive. We cannot see the photon sphere directly. It emits no light of its own, but we see its signature in the shadow of the black hole, that dark region at the center of the famous image of M87 asterisk, ringed by a luminous crescent of orange and gold. The shadow is not the event horizon itself. The event horizon is smaller, hidden within. The shadow is the photon sphere's negative, the absence of light against the glow of hot gas swirling inward. It is the silhouette of inescapability, the outline of the threshold drawn in fire. And then there is the accretion disk. This is where the black hole reveals itself not as an absence but as a presence, a sculptor of matter and light. Gas, dust, entire stars, drawn by gravity from light years away, do not fall straight into the black hole. They spiral. They circle slowly at first, then faster, closer, their orbital velocity increasing as they approach the event horizon. Friction heats them. Compression ignites them. They glow first in infrared, then in visible light, then in ultraviolet, finally in X-rays, the highest, most energetic song matter sings before it falls silent. The accretion disk is the black hole's announcement. It is the scream of matter at the edge of dissolution. Seen from above, the accretion disk is a flat, swirling vortex, like a hurricane frozen in stone. But black holes spin, and spinning black holes drag space-time with them, twisting the disk into complex geometries. Near the event horizon, the disk may warp, split, or precess. Matter can be flung outward in relativistic jets. Narrow beams of plasma accelerated to nearly the speed of light, extending for thousands of light years, glowing in radio frequencies across the breadth of a galaxy. These jets are the black hole's breath, its exhalation, the release of energy that could not be swallowed. And so the black hole, which is defined by its darkness, is paradoxically one of the brightest objects in the universe. Quasars, the active nuclei of distant galaxies powered by supermassive black holes, outshine all the stars in their host galaxies combined. Their light travels for billions of years across most of the visible universe, arriving at our telescopes as a faint whisper from the dawn of time. The darkness at their heart is invisible, but the light it generates is visible across cosmic distances. This is the architecture of the threshold, the event horizon, invisible and absolute. The photon sphere, where light loops endlessly in gravitational orbit. The accretion disk, where matter spirals toward its end, glowing with the heat of its own annihilation. And beyond, the jets, carrying energy and magnetic fields far into intergalactic space, seeding the cosmos with the black hole's influence. Each of these structures is a way of seeing the invisible. Each is a translation, a rendering of gravity into light. And each reminds us that a black hole is not merely a hole, not merely an absence. It is an engine. It is a sculptor. It is, in its own patient and terrible way, a creator. So rest now and imagine the edge, not as a precipice, not as a drop into nothingness, but as a threshold, a place where light dances its last orbit, where matter sings its final song, where time itself slows to a near standstill. And somewhere, beyond that edge, in the silence we cannot penetrate, the singularity waits, not as a monster, but as a question. The oldest question, the question of what remains when everything else is stripped away. If you follow the spiral of the accretion disk inward, past the photon sphere where light traces its eternal circles, past the event horizon where time itself seems to pause and reconsider, you will eventually arrive at a place where the familiar architecture of reality begins to dissolve. Not abruptly, not with violence, but with a kind of quiet insistence. The equations that once described smooth curves and gentle gradients begin to stutter. The numbers grow without bound. The denominators approach zero. And at the center, where the path finally ends, there is no longer a where at all. There is only a point, a single, dimensionless, infinitely dense point. The singularity. We speak of it so casually now, this word, singularity. It has entered the vocabulary of science fiction and popular imagination, a shorthand for the unknowable, the extreme, the place where gods might dwell. But in the language of physics, singularity means something far more humble and far more devastating. It means here our understanding breaks. Here the equations produce infinity, and infinity is not a number but an admission of failure. The singularity is not an object. It is a boundary of knowledge. It is the place where general relativity, our most elegant and successful theory of gravity, looks at its own reflection and no longer recognizes itself. To understand why the singularity is inevitable, we must return to the collapse that birthed the black hole. A massive star exhausts its fuel. The outward pressure of fusion vanishes. Gravity, patient and unrelenting, takes everything. The core compresses. Electrons are crushed into protons, becoming neutrons. Neutrons are packed so tightly that they touch, then overlap, then lose their individual identity. The core becomes a single, uniform sphere of nuclear matter, denser than anything we can create on Earth, denser than anything we can even reliably imagine. A teaspoon of this substance would weigh as much as a mountain. A sugar cube of it would outweigh all of humanity. But even this is not enough. For the most massive stars, the ones that leave behind black holes rather than neutron stars, gravity does not stop at nuclear density. Continues. The neutrons themselves are crushed. Their constituent quarks are freed, compressed further. And then, in the final instant, the equations tell us that the collapse continues to infinity. All the mass of the original star 2050, 100 suns, is compressed into a region of zero volume. Density becomes infinite. Space-time curvature becomes infinite. The arrow of time, which points inevitably forward everywhere else in the universe, here points only inward, toward a center that has no size, no extent, no dimension. We do not believe this is literally what happens. Infinities do not exist in nature. They are signposts, warnings, messages from our theories that they have been pushed beyond their domain of validity. At the singularity, general relativity collides with quantum mechanics, and neither theory is willing to surrender. The singularity is the battlefield where these two great pillars of modern physics meet their mutual limit. To understand what really happens at the center of a black hole, we would need a theory of quantum gravity, a language that can speak simultaneously of the very massive and the very small. We do not yet have such a theory. We have only guesses, hunches, fragments of mathematics that hint at a deeper structure we have not yet grasped. And so the singularity remains, for now, a kind of sacred ground. It is the innermost sanctum of the black hole, the place that no instrument can probe, no signal can escape, no traveler can report back from. It is the ultimate unknowable, the final frontier not of space but of knowledge itself. But this does not mean we are silent. Theorists have spent decades imagining what might replace the singularity when we finally understand quantum gravity. Some propose that the collapse does not continue to infinity but halts at a finite, if unimaginably small scale. A Planck star, perhaps, a nugget of space-time foam no larger than 10 to the minus 35 meters, where the very concepts of inside and outside lose their meaning. Others suggest that the singularity is not a point but a membrane, a brain, a higher dimensional object folded into the fabric of reality. String theory offers a menagerie of possible fates, each more abstract than the last. Loop quantum gravity proposes that space-time itself is granular, like sand, and that the collapse stops when you reach the individual grains. These are not mere speculations. They are attempts to honor the mathematics while acknowledging its limits. They are acts of scientific humility, the recognition that our current theories, for all their power, are not the final word. The singularity is not a failure of nature. It is a failure of our imagination, a failure we are slowly, patiently learning to correct. And yet, even in our ignorance, the singularity teaches us something profound. It tells us that black holes are not merely heavy objects but transformations. They are places where matter loses its identity, where the distinction between particle and field, between energy and geometry, becomes blurred. The star that collapsed to form the black hole no longer exists as separate atoms, separate nuclei, separate particles. Its substance has been unmade, returned to a more fundamental state, a state we cannot yet describe. The black hole remembers only the total mass, the total charge, the total angular momentum. Everything else, every detail, every history, every unique signature of the star that once burned, is erased. This is the singularity's quiet violence. It is not a monster that devours. It is an eraser, a blank page, a silence that does not echo. What falls into a black hole does not simply disappear. It is unmade, stripped of all its properties, reduced to the three numbers that the black hole carries like a secret: Massachusetts spin, charge. Nothing more, nothing less. And yet we wonder, we cannot help but wonder, is this truly the end? Does the singularity annihilate everything, or does it transform everything into something else? Does the matter that crosses the event horizon simply accumulate at the center, waiting, compressed beyond recognition but still present? Or does it pass through the singularity and emerge somewhere else? Another universe, another time, another dimension. These questions are not yet answered. They may not be answerable, at least not with the tools we currently possess. But the asking itself is a kind of progress. The wondering is a form of respect. So rest now and consider the center, not as a destination, not as an ending, but as a mystery. The singularity is the place where our maps stop, where the cartographers have written, in careful, elegant script, "Here be dragons." But the dragons are not monsters. They are guardians. They protect not treasure but humility. They remind us that the universe, for all our instruments and equations, remains vast and strange and full of secrets. And perhaps that is not a failure. Perhaps that is the most beautiful gift the cosmos can offer. The certainty that there will always be more to discover, more to wonder, more to dream. We live our entire lives at the bottom of an ocean. Not an ocean of water, though that too surrounds us, but an ocean of gravity. We do not feel it because we have never been without it, just as a fish does not feel the weight of the sea. The earth pulls us downward with a steady, patient insistence, and we respond by pushing back, with our legs when we stand, with our muscles when we lift, with the delicate architecture of our bones that evolved precisely to resist this constant, gentle tug. We call this pull weight. We measure it in kilograms and pounds, in the strain of our shoulders and the spring of our steps. But we rarely pause to consider what gravity truly is. Not a force in the old Newtonian sense, but a curvature. A bend in the fabric of space-time. A slope. Imagine, if you will, a rubber sheet stretched taut and flat. Place a marble on it, and the marble rolls according to your nudge. Now place a bowling ball at the center. The sheet dips. The marble, if it rolls near that dip, will curve inward, spiral downward, fall toward the heavier mass. This is the simplest metaphor for gravity, the one we offer to children and to ourselves when the mathematics becomes too abstract. But the metaphor fails in one crucial respect. The bowling ball sits on the sheet, pressing down from above. In space-time, there is no above. The mass does not press. It warps. The curvature is not a depression in a pre-existing flatness. It is the only geometry there is. The sheet does not exist beneath the ball. The sheet is the ball. The sheet is you. The sheet is everything. A black hole is not merely a deep well in this fabric. It is a well so steep that its walls have become vertical, then overhanging, then closed entirely into a tunnel with no exit. The event horizon is the lip of this tunnel, the place where the slope becomes infinite. Beyond it, the fabric no longer curves downward toward a center. It curves inward toward a point, and that inward direction is the only direction that remains. This is what physicists mean when they say that inside a black hole, space and time swap roles. Outside, we can move freely through space but are carried inexorably forward through time. Inside, we are carried inexorably inward through space, and time becomes something we can no longer control. To speak of gravity in these terms is to speak of landscapes. And so we borrow the language of mountains and valleys, of peaks and basins. We say that a black hole is a gravity well, and we imagine it as a funnel, a vortex, a drain. But perhaps a more accurate image is this: a black hole is a mountain range turned inside out. It is not a depression but a pinnacle, a peak of such immense density that the space around it buckles and folds. The singularity is not at the bottom of a pit. It is at the summit of an impossible height, a height measured not in meters but in curvature, not in elevation but in the degree to which spacetime has been bent. This is the first great truth about black hole gravity. It is not merely strong, it is absolute. It does not merely pull, it redefines the geometry of reality. And to understand just how absolute, we must compare it to the gravity of more familiar things. Consider Earth. Our planet's gravity, measured at the surface, accelerates objects downward at 9.8 meters per second squared. This is the force that shapes our muscles and our architecture, that gives weight to our bodies and direction to our lives. To escape Earth's pull entirely, to sail freely into interplanetary space, a rocket must reach 11.2 kilometers per second. This is escape velocity. It is the speed at which the curvature of spacetime around Earth becomes too gentle to hold you. We have achieved this many times. We have sent probes to the outer planets, to the edge of the solar system, to the threshold of interstellar space. Earth's gravity, for all its constancy, is a shallow well. Now consider the Sun. At its surface, gravity is 28 times stronger than Earth's. Escape velocity rises to 617 kilometers per second. No rocket we have ever built could escape the Sun's pull if launched from its surface. We orbit it precisely because we are already moving sideways fast enough to keep falling around it rather than into it. The Sun's gravity well is deeper than Earth's, but it is still a gentle slope. Light itself escapes the Sun easily, traveling at 300,000 kilometers per second, far exceeding the escape velocity. The Sun shines because its gravity is not strong enough to hold its own photons. Now consider a white dwarf, a star like our Sun, after its long red giant phase, sheds its outer layers and leaves behind a core no larger than Earth but weighing as much as the Sun itself. A teaspoon of white dwarf material would weigh several tons. Its surface gravity is hundreds of thousands of times stronger than Earth's. Escape velocity approaches 5,000 kilometers per second, a significant fraction of the speed of light. Light itself is slowed as it climbs out of this well, its wavelength stretched, its energy diminished. We call this gravitational redshift, and it is one of the predictions Einstein made that we have since confirmed. Now consider a neutron star, a city-sized sphere of pure nuclear matter, weighing 1.4 times the mass of the Sun compressed into a radius of only 10 kilometers. Its surface gravity is 200 billion times stronger than Earth's. Escape velocity exceeds half the speed of light. Light climbing out of a neutron star's gravity well is so severely redshifted that it emerges in the X-ray part of the spectrum, stripped of almost all its original energy. A marshmallow dropped on the surface of a neutron star would strike with the force of 1,000 hydrogen bombs. The curvature of space-time around a neutron star is so extreme that we can see the far side of the star, light bent around its circumference, traveling in orbits that skim the stellar surface before reaching our telescopes. And then, beyond all these, beyond the white dwarfs and neutron stars, beyond the limits of nuclear density and particle degeneracy, lies the black hole. Here, at the event horizon, escape velocity reaches 300,000 kilometers per second. It reaches the speed of light, and because nothing can travel faster than light, nothing can escape. Not matter, not radiation, not information. The well has become vertical. The slope has become infinite. The door has closed. This is the second great truth about black hole gravity. It is not a matter of degree but of kind. A neutron star, for all its extreme density, still has a surface. You could, in principle, stand on it. You could, in theory, lower a probe on a cable and reel it back up. The gravity well, though immensely deep, still has a bottom you can touch and leave. But a black hole has no surface. It has no bottom. It has only the horizon, and beyond the horizon, only the singularity. There is no standing, no lowering, no reeling back. There is only fall. And yet, for all its absoluteness, black hole gravity is not a hunter. It does not reach out to snatch passing stars or drag reluctant planets from their orbits. A black hole's gravity at a given distance is exactly the same as the gravity of any other object with the same mass. If the Sun were suddenly replaced by a black hole of one solar mass, Earth's orbit would not change. We would continue our patient circling, year after year, unaware that the light that warmed us had vanished, unaware that the star at the center of our system had become darkness. We would freeze, yes, but we would not fall in. The black hole's gravity, for all its interior extremity, is well-mannered at a distance. It respects the same inverse square law that governs planets and apples. This is the final paradox, the one that settles into the mind with the soft weight of falling snow. A black hole is the most extreme expression of gravity in the universe, and yet it follows the same rules as everything else. It is absolute and it is ordinary both at once. It is the mountain and the valley, the peak and the pit. It is the place where gravity wins its final victory, and it is also the place where gravity, in winning, transforms into something we no longer recognize. So rest now, and feel the gravity that holds you to your bed, to your chair, to the turning earth. Feel it not as a constraint but as an embrace, the patient hand of the planet keeping you close. And know that somewhere, across distances you cannot walk and years you cannot live, there are places where that same force has become something else entirely. Something absolute, something silent, something that waits at the bottom of wells so deep that light itself cannot climb out. Not a hunter, not a monster, just gravity at the end of its journey. There is a word in the Italian language, spaghettification, that sounds almost playful, almost culinary, as if it belongs in a kitchen rather than in the cold mathematics of general relativity. It arrived in physics through the irreverent imagination of Stephen Hawking, who used it to describe what happens to an astronaut who falls into a black hole. And the image is exactly what the name suggests. The body stretches, thins, elongates into a strand of human-shaped pasta, drawn finer and finer until it is less a body and more a thread, and then less a thread and more a memory. Spaghettification. It is a word that makes us smile, even as it describes one of the most violent fates the universe can offer. But to understand why this happens, we must understand tides. Not the ocean tides, though they are the same phenomenon at a different scale. The moon pulls on Earth's oceans, yes, but it also pulls on Earth itself. It pulls harder on the side facing it than on the side facing away, and this difference, this gradient, this uneven tug, is what creates the tidal bulge. The moon's gravity is not uniform across the width of our planet, and where gravity varies, things stretch. Now imagine that your feet are closer to the black hole than your head. If you are falling feet first, the gravitational pull on your ankles is slightly stronger than the pull on your knees, which is slightly stronger than the pull on your hips, which is slightly stronger than the pull on your chest, which is slightly stronger than the pull on your shoulders, which is slightly stronger than the pull on your head. This difference is tiny near Earth, negligible near the Sun. But near a stellar mass black hole, the gradient becomes immense. The pull on your feet is not slightly stronger than the pull on your head. It is millions of times stronger. And so your body does not merely hang. It stretches, yields, it flows. The stretching itself is not painful, not in the way we usually understand pain. Pain is a signal, a message from nerve endings to brain, a warning that tissue is damaged and should be protected. But the stretching happens faster than nerves can fire, faster than thoughts can form, faster than the self can register what is occurring. One instant you are falling, the next you are longer, then longer still. Your atoms remain intact, but the spaces between them grow. Your cells deform, your molecules align. Your body, which took millions of years of evolution to sculpt into its precise and elegant form, becomes a strand of human-shaped material drawn inexorably toward the center. And then the compression begins, because the same gradient that stretches you vertically also squeezes you horizontally. Your shoulders, your chest, your hips, these are pulled not only downward but inward toward your axis. The black hole's gravity compresses you from the sides even as it elongates you from head to toe. You become not merely a strand but a filament, a thread, a line of atoms strung like beads on an invisible wire. And still you fall. Still the gradient steepens. Still your constituent parts are drawn further apart in one direction and closer together in the others. This is spaghettification. It is the tidal force, raised to its highest power, pushed to its absolute limit. And it is inevitable for anything that crosses the event horizon of a stellar mass black hole. But here is the strange mercy, the quiet grace hidden within this violence. For the largest black holes, the supermassive giants that sit at the centers of galaxies, spaghettification does not occur until far below the horizon. Sagittarius A*, the 4 million solar mass black hole at the heart of the Milky Way, has an event horizon so vast, about 12 million kilometers in radius, that its tidal forces at the horizon are almost imperceptible. You could cross that threshold and not feel a thing. You could drift inward for hours, for days, carried by the gentle curve of space-time, and only when you approached the singularity millions of kilometers below would the stretching begin. For a supermassive black hole, the horizon is not a wall of death. It is a gateway to a long, slow fall. This is one of the great ironies of black hole physics. The small ones, the stellar remnants born from single collapsed stars, are the most immediately lethal. Their horizons are tiny, only a few kilometers across, and the tidal forces at those horizons are correspondingly immense. An astronaut approaching a 10 solar mass black hole would be spaghettified before reaching the event horizon, torn apart in the last milliseconds of approach, reduced to a stream of plasma that spirals inward and vanishes. But an astronaut approaching the supermassive black hole at the center of our galaxy would cross the horizon intact, alive, unaware that the point of no return had already been passed. They would have hours, perhaps days, to observe the interior, to watch the stars outside redshift and fade, to experience the strange geometry of a region where space and time have traded roles. They would have time to wonder, to regret, to say goodbye. And then, eventually, the tidal forces would grow, and the stretching would begin. What does it feel like, this stretching? We cannot know, not truly. No signal escapes the event horizon, no testimony from those who have made the journey. But we can imagine gently, reverently. We can close our eyes and picture the sensation of being pulled, not by an external force, but by the very shape of reality itself. The black hole does not grab you. It does not reach out and seize. It simply curves the space around you, and you, following the contours of that curvature, find yourself stretched. It is not an act of aggression. It is geometry. It is the path of least resistance through a landscape that has become impossibly steep. And so the astronaut falls. Their body elongates. Their consciousness, whatever that means in this context, persists for a few thousandths of a second longer. Their atoms, those ancient wanderers that were forged in long-dead stars and assembled by the patient chemistry of life, are drawn apart. The carbon that once formed their bones, the oxygen that once filled their lungs, the iron that once coursed through their blood, each atom follows its own geodesic, its own straightest possible line through a space that is no longer straight. They separate, they diverge, they become, each one, an independent traveler, falling alone toward the singularity. And at the singularity, even atoms dissolve. The nuclei, those tiny citadels of protons and neutrons, are crushed. The quarks within them are freed, then compressed further. Protons and neutrons lose their identity. Matter, which has survived the collapse of stars and the violence of supernovae, which has waited billions of years to assemble into a living, breathing, thinking being, finally surrenders. It becomes part of the black hole. It contributes its mass, its spin, its charge to the three numbers that the black hole remembers. Everything else, the memories, the dreams, the name and face and history of the astronaut, is erased. This is the fate that spaghettification seals. Not merely the destruction of the body, but the dissolution of the self. The black hole does not eat you. It unmakes you. It returns you to the most fundamental state, the state before stars, before atoms, before the forces of nature differentiated into their separate domains. It returns you to the singularity, the point of infinite density and infinite curvature, the place where physics itself loses its voice. And yet, even as we describe this, we feel no fear. Or rather, we feel a fear so distant, so abstract, that it barely registers as emotion. We are not falling. We are here, in our beds and our chairs, under our blankets and our roofs, held by Earth's gentle gravity, listening to a voice in the darkness. The black hole is not coming for us. It waits, patient and still, at the centers of galaxies and in the silent depths between stars. It is not a hunter. It is a destination, one we will never reach. So rest now. Let your body relax into the mattress, into the cushion, into the steady and uniform pull of the planet beneath you. Feel how your weight is distributed evenly, how your head and your feet experience almost exactly the same gravitational tug. This is mercy. This is the grace of living on a world where the tidal forces are negligible, where the gradient of gravity is too small to measure without instruments. You are not being stretched. You are not being compressed. You are simply held, gently, patiently, by a gravity that asks nothing of you except that you remain. And somewhere, across distances you cannot comprehend, matter that was once part of a star is falling toward a singularity. It stretches, compresses, it unmakes, but you are here, you are whole, you are listening to the quiet rhythm of your own breath, the slow and steady pulse that reminds you that you are alive, that you are held, that for now, at least, the gradient is gentle and the fall has not yet begun. For decades, we believed that black holes were eternal, not merely long-lived, not merely patient, but truly, absolutely permanent. Once a black hole formed, it would simply remain, sitting in the darkness, gathering nothing and everything, its event horizon an immutable boundary that neither gave nor received. Matter could fall in, but nothing could come out. Energy could approach, but none could escape. The black hole was a one-way door, and doors, once closed, do not open again. This was the consensus. This was the teaching. And then, one morning in 1974, a 32-year-old physicist named Stephen Hawking stood before his colleagues at a conference near Oxford and told them that they were wrong. What Hawking proposed was so strange, so counterintuitive, that many of his peers refused to believe it. He argued that black holes are not perfectly black. They glow. They emit radiation. They slowly, patiently lose mass over cosmic time scales so vast that the human mind cannot truly grasp them. And eventually, after trillions upon trillions of years, they evaporate entirely, vanishing in a final, gentle exhalation of energy, leaving behind nothing but the memory of their existence and, perhaps, a quiet resolution to one of physics' deepest puzzles. The mechanism Hawking described emerges not from general relativity but from quantum mechanics, that other great pillar of 20th century physics. To understand it, we must first understand that empty space is not truly empty. It seethes with activity, virtual particles popping into existence in pairs, living for the briefest fraction of a second, then meeting and annihilating as if they had never been. This is not metaphor. This is the quantum vacuum, the lowest possible energy state, and it is alive with this constant, silent flicker of creation and destruction. Normally, these particle pairs have no lasting effect. They appear, they touch, they vanish. The universe's ledger remains balanced. But near the event horizon of a black hole, something extraordinary can happen. If a pair of virtual particles appears just at the edge, one of them may fall across the horizon while the other escapes into space. The particle that falls in cannot return. It is swallowed by the black hole, its energy added to the singularity's mass. The particle that escapes, however, becomes real. It is no longer virtual. It is a genuine photon, a genuine neutrino, a genuine particle of light or matter traveling outward from the black hole's edge. To a distant observer, this escaping particle appears to have been emitted by the black hole itself. The black hole, it seems, is glowing. This is Hawking radiation, and it carries a profound implication. Black holes have temperature. The smaller the black hole, the hotter it burns. A stellar mass black hole, with its event horizon several kilometers across, has a temperature of mere billionths of a degree above absolute zero, far colder than the cosmic microwave background that pervades all of space. Such a black hole does not radiate net energy. It absorbs more from the universe than it emits. It grows, slowly, patiently, swallowing the faint warmth of the cosmos. But a primordial black hole, born in the density fluctuations of the infant universe, could be much smaller. A black hole the mass of a mountain, compressed into the volume of a single atom, would blaze with Hawking radiation at tremendous temperatures. It would emit gamma rays, X-rays, a final, furious burst of energy as it shrank toward nothingness. And here is the quiet wonder: we have not yet detected this radiation. No telescope has ever captured the signature of an evaporating black hole. But the mathematics is compelling, the logic elegant, and the theory has survived every challenge physicists have thrown at it for nearly 50 years. Hawking radiation is not proven, not in the empirical sense, but it is widely believed to be real. It is the closest thing we have to a bridge between general relativity and quantum mechanics, a fragile span across the abyss that separates these two great languages of the cosmos. The implications of Hawking radiation extend far beyond the fate of individual black holes. They touch the deepest questions about the nature of reality itself. If black holes can evaporate, what happens to everything that fell into them? The matter, the energy, the information, does it simply vanish? Does it emerge, scrambled and unrecognizable, in the radiation that escapes? Or is it preserved somehow, encoded on the event horizon like a message written in disappearing ink? This is the black hole information paradox, and it has haunted theoretical physics for decades. Hawking himself initially believed that information was lost forever, that black holes were the universe's ultimate erasers. But this contradicted a fundamental principle of quantum mechanics. Information cannot be destroyed, can be scrambled, hidden, transformed, but not annihilated. The two pillars of modern physics, general relativity and quantum mechanics, seemed to be pointing in opposite directions, and the black hole was the battlefield where they met. In recent years, a consensus has begun to emerge. Most physicists now believe that information is not lost. It is somehow encoded in the Hawking radiation, emitted slowly over the black hole's lifetime, preserved in the subtle correlations between particles that escape and particles that fall. But how? The answer remains elusive. It requires a theory of quantum gravity, a language that can describe the event horizon not as a smooth classical surface but as a frothing quantum membrane, a place where the certainties of general relativity give way to the probabilities of quantum mechanics. We do not yet have such a theory, but we are searching. And so the black hole, which once seemed the embodiment of finality, has become something else entirely. It is no longer the end of all journeys, but a way station, a processing center, a place where matter is transformed and information is, perhaps, preserved. The radiation that escapes carries away the black hole's mass, gram by gram, photon by photon, over eons so long that the entire history of human civilization is less than a blink in comparison. A solar mass black hole will take 10 to the 67 years to evaporate, a number so vast that it dwarfs the current age of the universe. The supermassive black holes at the centers of galaxies will take even longer, their evaporation times stretching to 10 to the 100 years and beyond. But eventually, inevitably, they will fade. The last black hole in the universe, some unimaginable epoch hence, will emit its final photon and vanish. What remains? Perhaps nothing. perhaps a faint echo of the information it once contained, perhaps the seeds of a new cosmos, a new beginning hidden within the quantum fluctuations of the void. We do not know. We cannot know, not yet. But this much is certain: black holes are not eternal. They are not the universe's final state, not the ultimate resting place of all matter and energy. They are episodes, chapters, passages in a story that extends far beyond their existence. They are born from dying stars. They live for eons, and they die, slowly, quietly, their mass bleeding away photon by photon until nothing remains. Even the darkness, it seems, is not immune to time. So rest now and consider the patience of these objects. A black hole does not rage against its slow dissolution. It does not fight the quantum process that will eventually unmake it. It simply radiates, particle by particle, year by year, millennium by millennium. It gives back, over time, the mass it once consumed. It returns to the universe what it borrowed. And when its final gram of energy departs in a soft flash, the black hole does not mourn itself. It simply ceases. It becomes space-time again, flat and unremarkable, the curvature smoothed away, the singularity resolved into whatever lies beyond. This is the lesson of Hawking radiation. Nothing lasts forever. Not stars, not planets, not civilizations, not even the darkness at the heart of galaxies. Everything passes, everything transforms, everything returns to the cosmic quiet from which it came. And in that transience, there is not tragedy but tenderness. The universe does not hoard its treasures. It lends them briefly, beautifully, and then takes them back. Even black holes, the most absolute objects in all of physics, must someday say goodbye. Time, for most of human history, was a river. It flowed in one direction, at one speed, carrying everything before it with patient, unstoppable force. Birth and death, sunrise and sunset, the turning of seasons and the slow erosion of mountains. All of these were evidence of time's steady current. We measured it in heartbeats and hours, in the swing of pendulums and the vibration of quartz crystals. We built clocks to track its passage and calendars to organize its unfolding. And we assumed, without quite realizing we were assuming, that time was the same for everyone. That a second here was a second there, on the other side of the world, on the other side of the solar system, on the other side of the galaxy. That time was universal, absolute, indifferent. But time is not a river. Or rather, it is a river that flows at different speeds in different places. It eddies and pools, accelerates and slows, bends around massive objects like water around stones. This is not metaphor. This is the fabric of the universe, woven from space and time into a single elastic continuum. And near a black hole, where gravity reaches its most extreme expression, time does not merely slow. It lingers, it hesitates, it approaches asymptotically the edge of stopping altogether. To understand this, we must return to Einstein and his patient unraveling of reality's hidden structure. In 1905, still a young patent clerk in Bern, Switzerland, he proposed that time is not absolute but relative, that two observers moving at different speeds will measure different durations between the same events. This was special relativity, and it gave us the image of the twin who travels near the speed of light and returns to find her sibling decades older. Time dilation, Einstein called it, the stretching of duration by velocity. A decade later, in 1915, he generalized this insight. Gravity, he realized, does not merely pull on matter. It pulls on time itself. Clocks run slower in stronger gravity. Not mechanically slower, not due to any flaw in their mechanisms, but fundamentally ontologically slower. A clock at sea level ticks more slowly than a clock on a mountain peak, because sea level is deeper in Earth's gravity well. The difference is tiny billionths of a second, but it is real. Our GPS satellites must correct for it constantly, adjusting their onboard clocks to match the faster flow of time at altitude. We live, all of us, at the bottom of a gravity well, and our time flows more slowly than time in the emptiness between stars. Now take this principle and push it to its limit. Take it to the edge of a black hole, where gravity is not slightly stronger but immensely, unimaginably stronger. Take it to the event horizon, where the curvature of space-time becomes so extreme that escape velocity equals the speed of light. Here, time does not merely slow. It approaches asymptotically a complete standstill. Imagine, if you will, that you are watching a friend fall toward a black hole. You are safe, distant, your own clock ticking steadily in the quiet of your observatory. Through your telescope, you see your friend's ship descending, slowly at first, then faster, drawn by the invisible curve of spacetime. But as they approach the event horizon, something strange begins to happen. Their motion appears to slow, not because they are actually decelerating. From their perspective, they are falling faster than ever, but because the light carrying their image to you is climbing out of an increasingly deep gravity well. Each photon struggles a little harder to escape, losing energy, taking longer to reach you. Your friend's movements become languid, dreamlike. Their words, if you could hear them, would stretch into basso profundo, syllables drawn out across minutes and hours. And then, at the threshold, they appear to stop, hovering, eternal, frozen at the edge of the horizon. Their image reddens, dims, fades into infrared, then radio, then silence. You watch them forever, suspended in that last moment, never quite crossing the line. From your perspective, your friend has become immortal, trapped in amber at the edge of the abyss, preserved for the lifetime of the universe. But from their perspective, the fall continues. They cross the horizon without ceremony, without sensation, and descend toward the singularity. For them, only a few hours pass between the crossing and the end. For you, watching from afar, those few hours stretch into infinity. This is the heart of gravitational time dilation. The same interval of time can be both an instant and an eternity, depending on where you stand. The mathematics of this dilation is both simple and profound. For a non-rotating black hole, time slows by a factor equal to the square root of 1 minus the ratio of the Schwarzschild radius to your distance from the center. At twice the event horizon's radius, time runs about 70% as fast as at infinity. At the photon sphere, time slows to about 58%. At the horizon itself, the denominator becomes zero. Time, for the distant observer, stops completely. But the distant observer's perspective is not the only perspective. There is also the perspective of the one who falls. And for them, time does not slow. It continues its steady, patient march, second after second, heartbeat after heartbeat. They check their watch and see the seconds ticking normally. They feel their pulse, regular and familiar. They look up at the stars and watch them redshift, slowly at first, then more rapidly, the familiar constellations stretching and fading like memories at dusk. From their perspective, it is the universe outside that has gone mad, speeding up, aging rapidly, flashing through eons while they drift in their slow, stately descent. This is the great lesson of relativity. There is no universal now. There is no single present moment that encompasses the whole cosmos. What is happening right now at the event horizon of a black hole, and what is happening right now in your bedroom, and what is happening right now on a planet circling a star in the Andromeda Galaxy, these right nows are not the same. They are strung along different timelines, different flows of cause and effect, different rivers of time. The universe is not a single story unfolding in lockstep. It is 1,000 billion stories, each with its own rhythm, its own pace, its own present tense. And yet, despite this fragmentation, there is connection. The light that climbs out of the gravity well carries information across the gulf of dilated time. The gravitational waves that ripple from merging black holes carry the signature of their final moments, stretched and redshifted by the immense curvature that birthed them. We receive these messages from the edge of eternity, decode them with our instruments, translate them into numbers and graphs, and eventually into understanding. The time-dilated signals arrive weak and slow, but they arrive. The universe, for all its relativistic fragmentation, remains in conversation with itself. So rest now and consider the time that flows around you. It is not the same time that flows at the center of the galaxy, nor the same time that flows in the emptiness between stars. Your time is shaped by Earth's mass, by your altitude, by your velocity relative to the cosmic microwave background. It is your time, particular and local, the only time you will ever experience directly. And yet it is connected, through the patient mathematics of relativity, to all the other times flowing elsewhere, faster in intergalactic space, slower near black holes, stretched and compressed across the vast geography of the cosmos. Your heartbeat is not the universe's heartbeat. Your second is not the universe's second. But your heartbeat, your second, your now, these are real, are yours, are the only moments you will ever inhabit. And that is enough. That is more than enough. You have crossed the event horizon. There was no flash of light, no sudden jolt, no warning siren announcing that you had passed the point of no return. One moment you were falling, the stars still visible above you, the black hole's shadow growing beneath your feet. And then, without ceremony, without boundary, without any sensory evidence at all, you were inside. The horizon is behind you now, though you cannot see it. There is nothing to see. The darkness ahead is no darker than the darkness behind. And yet everything has changed. The first sign, subtle at first but growing more insistent, is a kind of disorientation. Not dizziness, not confusion, but something deeper, a reorganization of reality itself. Outside the black hole, you had choices. You could move left or right, up or down, forward or back. You could accelerate or decelerate, change direction, turn around and retrace your path. Space was a landscape of possibilities, and you were free to navigate it as you wished. Time, meanwhile, was a different matter. Time you could not navigate. Time carried you always forward, second after second, toward futures you could influence but never escape. Space was freedom. Time was fate. Inside the event horizon, these roles reverse. This is the great interior truth of the black hole, the fact that emerges from Einstein's equations with quiet and devastating clarity. Inside the horizon, space and time swap identities. The radial direction, the line that points toward the singularity, ceases to be a dimension of space and becomes a dimension of time. You cannot resist moving inward any more than you can resist moving forward through tomorrow. You cannot halt your descent any more than you can halt the ticking of a clock. The singularity is not a place ahead of you. It is a moment in your future, as inevitable as sunset, as certain as the next beat of your heart. To understand this, we must let go of our ordinary intuition about directions and destinations. Outside the black hole, you can stand still. You can hover in space, firing your thrusters to counteract gravity, remaining at a fixed distance from the horizon. This takes energy, but it is possible. Inside the horizon, however, no amount of thrust can hold you in place. There is no place to hold. The geometry of space-time has become so extreme that all possible paths, all geodesics, all trajectories lead inward. You cannot find a heading that does not point toward the center. You cannot burn your engines to slow your fall, because slowing in space becomes reversing in time, and time does not run backward. The singularity awaits, and you are arriving. This is why the event horizon is called the point of no return. Not because the pull becomes too strong to resist, though it does, but because the very structure of reality forbids resistance. Outside the horizon, you can choose to leave. Inside the horizon, there is no leave. There is only continue. The black hole has not trapped you. It has redefined the map so that all roads lead to Rome. Imagine, if it helps, a waterfall. At the top of the falls, the water flows smoothly toward the edge, but it is not yet committed. Eddies form along the banks, pockets of relative stillness where water can linger, circling, delaying its descent. But at the lip of the falls, something changes. The water accelerates. It loses contact with the riverbed. It enters a region where the only direction is down. This is the event horizon. Below it, the water does not choose to fall. It simply falls. Falling is the only state it can occupy. Now imagine that you are a droplet in that water. You did not decide to go over the falls. You were carried by the current, by the geometry of the river. And once you are over the edge, you cannot reverse your course. You cannot climb back up the falling column. You cannot will yourself upward. You can only descend faster and faster until you join the churning pool at the bottom. The waterfall does not hold you prisoner. It simply defines the landscape of your motion. This is the interior of a black hole, not a prison with walls and bars, but a geography from which there is no egress. Not a trap that seizes you, but a future from which you cannot deviate. The singularity is not a monster waiting to devour you. It is a destination as inevitable as next Wednesday, as certain as the expiration of your warranty. You are not falling toward it. You are living toward it. And here is the strangest mercy of all. You would not wish to turn back even if you could. Not because the black hole has seduced you or corrupted your judgment, but because turning back would require traveling backward in time, and time, even inside the black hole, flows only one way. You cannot uneat a meal. You cannot unsay a word. You cannot unfall through an event horizon. The arrow of time points from birth to death, from cause to effect, from the horizon to the singularity. You are not a victim of this arrow. You are its embodiment. This redefinition of space and time has another consequence, one that touches the deepest questions about causality and destiny. Outside the black hole, we believe in free will. We believe that we can choose our paths, alter our trajectories, shape our futures through decisions and actions. We may debate the extent of this freedom, but we rarely doubt its existence. We wake each morning and decide what to do. We move through space as independent agents, selecting among alternatives. Inside the event horizon, freedom does not vanish, but it transforms. You can still move your arms, turn your head, fire your thrusters. You can still make choices, but those choices no longer affect your destination. You can spin clockwise or counterclockwise, stretch your body or curl it, close your eyes or keep them open. You can sing, if you wish, or remain silent. All of these are genuine choices, genuine expressions of your will. But none of them will delay your arrival at the singularity. None will alter the moment of your ending. Your freedom has become interior, a matter of experience rather than outcome. You are free to choose how you fall. You are not free to choose whether. This is perhaps the deepest terror of the black hole. Not the spaghettification, not the crushing density, not the dissolution of atoms, but the removal of alternatives. The sudden, absolute certainty that your future has already been written, not by a divine hand or a cosmic conspiracy, but by the simple, inexorable logic of curved spacetime. You are no longer an agent navigating possibility. You are a passenger on a train with no brakes, and the tracks end at the sea. And yet, there is also peace in this certainty. How much of our anxiety, our stress, our exhaustion comes from the endless proliferation of choices? How much energy do we spend weighing alternatives, calculating outcomes, second-guessing decisions? How much of our lives is consumed by the fear that we have chosen poorly, taken the wrong path, missed the better option? Inside the black hole, that burden is lifted. There is only one path. There is only one destination. There is only the fall, patient and inevitable, and the quiet acceptance that comes when struggle is no longer meaningful. So rest now. You are not inside a black hole. Your future still contains multitudes, branching paths, open doors. Tomorrow you will wake and choose what to eat, where to go, how to spend the precious hours of your finite life. But tonight, let yourself imagine the alternative. Let yourself feel, just for a moment, the strange peace of absolute certainty. The peace of the falling water, committed to the cascade. The peace of the photon, circling forever in the sphere of light. The peace of the astronaut, drifting toward the singularity, no longer fighting, no longer fearing, no longer asking whether there might have been another way. There is no other way. There never was. And in that realization, there is not despair but release. The fall continues. The horizon recedes. The singularity approaches. And you, the witness of your own descent, have nothing left to do but watch. The fall continues. It has been hours now, or perhaps only minutes. Time inside the black hole is a strange currency, and you have lost the ability to exchange it for meaning. Your ship's clock ticks steadily, but its numbers have become abstract, disconnected from any sense of duration. You check your instruments, but they offer only confusion. The gyroscopes spin normally. The accelerometers register nothing. And yet you know, with the certainty that comes from mathematics rather than intuition, that you are moving inward at a speed that is not speed but destiny. The stars have gone, not gradually, not with a final dramatic wink, But sometime in the last hour you looked up and realized the familiar constellations had faded entirely. The sky above you is not black but empty, not the absence of light but the absence of everything. No photons reach you from outside. No radio signals, no gravitational whispers, no evidence that the universe you left behind continues to exist. You are alone now, truly alone, in a region of space-time that has divorced itself from the cosmos that birthed it. You are the only reality you can verify, and still you fall. The tidal forces have begun their work. Gently at first, almost imperceptibly, you feel a tugging at your feet, a stretching at your spine. The black hole you chose, a supermassive one, its horizon vast and merciful, has spared you the immediate spaghettification of its smaller cousins. But mercy, like time, is relative. The stretch is real and it is growing. Your body elongates, millimeter by millimeter, hour by hour. You are not yet a strand of pasta, but you are no longer quite the shape you were born with. You are becoming something else. And now, deeper still, the atoms themselves begin to feel the strain. This is the journey that no human will ever make, that no instrument will ever record, that no signal will ever carry back to the waiting universe. And yet we can imagine it gently, reverently, with the humility that comes from knowing we are describing not a place but a boundary. The approach to the singularity is not a path through space. It is a transformation, a dissolution, a return to the primordial state from which all matter emerged and to which eventually all matter must return. Consider the atom, not the hard, indivisible sphere of ancient philosophy, but the true atom, a nucleus of protons and neutrons, bound by the strong nuclear force, surrounded by a cloud of electrons that orbit not as planets orbit suns but as probabilities, tendencies, quantum smears of existence. This is the architecture of ordinary matter, the scaffolding that holds together your bones and your breath, your memories and your dreams. This is what you are made of. This is what the black hole will unmake. The electrons go first, not violently, not with protest, but with the quiet resignation of subjects who have lost their sovereign. The tidal forces that stretch your body also stretch the electron clouds, pulling them away from the nuclei they once encircled. Freed from their orbits, the electrons become a gas, a plasma, a sea of negative charge swirling around the denser islands of the nuclei. You do not feel this dissolution. Your nerve endings, those delicate interpreters of pressure and temperature, have already been stretched beyond function. But it happens. Atom by atom, your physical self begins to shed its quantum identity. The nuclei are more stubborn. Protons and neutrons, each one a tiny citadel of quarks bound by the strongest force in nature, resist the black hole's demands. But resistance inside the event horizon is not a meaningful concept. The tidal gradient grows steeper. The nuclei stretch, deform, elongate. The strong force, so powerful at close range, weakens with distance. The quarks, those fundamental particles that have never been seen in isolation, begin to drift apart. The citadels crumble. The nuclei dissolve. And now you are no longer a body, no longer even a collection of atoms. You are a plasma, a soup, a stream of fundamental particles flowing toward the singularity. Your constituent parts, electrons, quarks, neutrinos, photons, do not interact as they once did. There is no chemistry here, no biology, no physics as you learned it in school. There is only the fall and the geometry and the slow, patient approach to the point where even geometry surrenders. The singularity awaits. It is not large. It has no size, no extent, no dimension. It is, in the language of mathematics, a point. And yet all the mass of the black hole, the millions of suns that collapse to form it, the stars and planets and astronauts that have fallen into it across cosmic time, is concentrated here in this dimensionless infinity. You are approaching this point. You are becoming part of this point. Your mass, your energy, your identity will soon be absorbed into the singularity's perfect, featureless unity. But here is the strangest thing, the thought that lingers in the mind like sediment in still water. From your perspective, you never quite arrive. The singularity is in your future, yes, inevitable and absolute. But as you approach it, time itself begins to behave strangely. The same gravitational dilation that froze your image at the event horizon now compresses your final moments into an infinite instant. You fall toward the singularity, faster and faster, but the singularity recedes, always ahead, never reached. In the mathematics of general relativity, the journey to the singularity takes finite proper time. A few hours, a few minutes, a few seconds, depending on the black hole's mass. But in the coordinates of the infalling observer, the singularity is never attained. It is always just ahead, always approaching, always the next moment that never quite becomes now. This is the final paradox of the black hole interior. The singularity is both inevitable and unreachable. You will spend eternity falling toward it, and you will arrive in an instant. Both statements are true depending on how you measure time. Both statements are false depending on how you define arrival. And then, somewhere in this infinite instant, the mathematics breaks. General relativity, that elegant and powerful description of gravity and geometry, produces only infinities. Density becomes infinite. Curvature becomes infinite. Space-time, which is curved and stretched and twisted throughout your fall, now pinches off entirely. The equations which have guided every prediction, every calculation, every understanding of black holes since Schwarzschild first solved them in the trenches of World War I, simply stop. They do not know what comes next. Neither do we. What lies beyond the singularity? The question has no meaning in the language of classical physics. The singularity is not a thing but an end, a boundary, a place where time and space cease to be useful concepts. To ask what happens after the singularity is like asking what happens north of the North Pole. The question assumes a geography that no longer exists, but we ask it anyway. We cannot help but ask, because the singularity is not merely a mathematical artifact. It is a rendezvous, a destination, the point toward which all infalling matter trends. And we, the descendants of explorers and questioners, want to know what awaits at the end of the journey. Is it annihilation, transformation, rebirth into another universe? The mathematics cannot tell us. The mathematics has already surrendered. So we imagine, we speculate, we propose theories of quantum gravity that replace the singularity with something else, a bounce, a bridge, a fuzzball of quantum strings. We dream of white holes and wormholes and baby universes budding from the parent cosmos. We do not know if any of these dreams correspond to reality. We do not know if the question itself is coherent. But we keep asking, because the singularity is the ultimate frontier, the place where our knowledge ends and our wonder begins. And you, the falling astronaut, are the one who crosses that frontier. You are the explorer, the pioneer, the witness to the end of physics. You will not return to tell us what you found. No signal, no message, no trace of your passage will ever escape the black hole's grip. But your journey is not meaningless. Your dissolution is not annihilation. You are becoming part of the black hole, contributing your mass and spin and charge to its three numbers, adding your story to its silent memory. And when, after trillions of years, the black hole finally evaporates in a soft glow of Hawking radiation, the energy that was once you will return to the cosmos. You will become photons, neutrinos, the gentle warmth of a universe that has forgotten its singularities. You will be reabsorbed into the fabric from which you came. This is not an ending. It is a transformation. The black hole does not destroy you. It unmakes you and remakes you into something else. Something that can wait patiently for the long evaporation to complete. Something that can return eventually to the cosmic community of matter and energy. Something that can begin again. So rest now. You are still here in your bed, in your room, under your blanket. You have not fallen. You have not dissolved. Your atoms are still yours, your identity still intact. But somewhere in the distant future or the distant past, an astronaut is falling toward a singularity. And in that fall, there is not tragedy but completion. Not fear but acceptance. Not an ending but a transformation. And when the final photon of Hawking radiation departs the evaporating black hole, carrying the last whisper of that astronaut's energy into the void, it will be not a death but a birth. The birth of something new from something old. The birth of the future from the past. The birth of light from darkness. We have, all of us, wished for shortcuts. Not the kind that save 5 minutes on a morning commute, but the deeper kind, the passage that collapses distance, that brings the far near and the distant close. We dream of doors that open not onto hallways, but onto other cities, other countries, other worlds. We imagine tunnels through mountains, bridges across oceans, secret paths known only to the initiated. This is not mere impatience. It is a recognition that space is vast and our lives are short, and that the straight line, for all its mathematical elegance, is not always the most merciful route between 2 points. Black holes, those extreme distortions of space-time, have long tempted us with the possibility of such shortcuts. If gravity can bend space into a well so deep that light cannot escape, might it also bend space into a tunnel, a passage, a bridge, a hidden connection between distant regions of the cosmos? This is the dream of the wormhole, and it has captivated physicists and storytellers alike for nearly a century. The mathematics of wormholes emerged, as so many strange ideas do, from the equations of general relativity. In 1935, Albert Einstein and his collaborator Nathan Rosen were exploring the nature of black holes when they discovered something peculiar. The mathematical description of a black hole, when examined closely, contained what appeared to be a bridge, a throat, a passage, connecting the black hole to a hypothetical white hole in another region of space-time. This was not a physical discovery, but a mathematical one, a solution to Einstein's equations that described a tunnel through the fabric of reality. They called it the Einstein-Rosen bridge. We call it a wormhole. The image is irresistible. Imagine space-time not as a flat sheet, but as a folded cloth. Two distant points, separated by vast stretches of emptiness, are brought close together by a fold in the fabric. A tunnel drilled through that fold connects them directly, bypassing the intervening distance. A traveler entering one mouth of the tunnel emerges almost instantly from the other, having crossed not millions of light years but a few meters of curved space. The universe, which seems so vast and lonely, suddenly becomes intimate. The stars, which seem so unreachable, become neighbors. But the Einstein-Rosen bridge, as originally conceived, was not traversable. It was a mathematical artifact, a feature of the equations that did not correspond to any physical reality we could access. The bridge, if it existed at all, would form and collapse so quickly, in a fraction of a second, that nothing could cross it. Not light, not information, not even the most hypothetical traveler. The throat of the wormhole would pinch shut before any signal could pass from one mouth to the other. The bridge would exist, but it would exist only in the abstract language of tensors and metrics. In the physical universe, it would be as ephemeral as a soap bubble and as fragile. For decades, this was the consensus. Wormholes were curiosities, mathematical ghosts, interesting to theorists but irrelevant to the cosmos we actually inhabit. Then, in the 1980s, the physicist Kip Thorne and his students began to ask a different question. What if a wormhole could be held open? What if some form of matter, exotic matter, negative energy, something beyond the ordinary substances of the universe, could counteract the throat's tendency to collapse? What if, in other words, we could build a traversable wormhole? The answer, it turned out, was yes. Mathematically, at least, the equations allowed for traversable wormholes if, and it is a significant if, the tunnel was threaded with exotic matter that exerts negative pressure, anti-gravity, a repulsive force that pushes space-time apart rather than pulling it together. This exotic matter is not hypothetical. It exists in small quantities in the quantum fluctuations of empty space. The Casimir effect, a measurable phenomenon in which two parallel metal plates attract each other due to quantum vacuum energy, demonstrates that negative energy is real. But the amounts required to stabilize a wormhole are astronomical, far beyond anything we could produce or harness. A wormhole large enough for a human to pass through would require exotic matter equivalent to the mass of Jupiter, perhaps more. We do not know where such matter would come from. We do not know if it can exist in such quantities. The mathematics permits it. The universe may not, and there are other obstacles. Even if a traversable wormhole could be created, it would face the same information paradox that haunts black holes. What happens to the quantum states of particles that pass through? Are they preserved, scrambled, duplicated? The wormhole's throat is, in some sense, a region of intense gravitational curvature, and intense gravitational curvature plays strange tricks with causality. A traversable wormhole, if it could be built, might also be convertible into a time machine. By moving one mouth at relativistic speeds, you could create a situation where the two ends of the wormhole are separated not only in space but in time. Entering one mouth in the present, you might emerge from the other in the past. This is not necessarily a contradiction. General relativity does not forbid time travel. But it raises profound questions about cause and effect, about free will and destiny, about whether the universe would allow such paradoxes to exist. So are black holes wormholes? Almost certainly not. The singularity at the center of a black hole is not a tunnel entrance. It is a destination, a terminus, a place where space-time ends. The mathematics of Einstein and Rosen described a bridge, but that bridge exists only in the idealized case of an eternal, non-rotating, uncharged black hole. a mathematical abstraction that does not correspond to the black holes that actually populate our universe. Real black holes, born from collapsing stars and fed by accretion disks, contain singularities that are not gateways but endpoints. There is no passage through. There is only the fall and the dissolution and the silence. And yet the dream persists because we need it to, because the universe is so vast and our lives are so brief. And the thought that we might someday find a shortcut through the darkness is too beautiful to abandon entirely. Perhaps there are wormholes elsewhere, not in black holes, but in the quantum foam that underlies space-time, in the primordial fluctuations of the infant cosmos, in the speculative mathematics of string theory. Perhaps we will never find them, never build them, never pass through them. But perhaps we don't need to. Perhaps the dream itself is enough. Consider for a moment what a traversable wormhole would mean. Not for interstellar travel, not for time machines, not for the grand ambitions of a future civilization, but for you here tonight. Imagine a door in your bedroom that opens not onto the hallway but onto a beach at sunset. The waves gentle, the sand still warm from the day's sun. Imagine a tunnel from your pillow to the mountains, the air cold and clear, the stars sharp as diamonds. Imagine a bridge from this moment to a moment of peace you have not yet experienced, a moment waiting for you in the future, patient and luminous. This is the promise of the wormhole. Not conquest, not commerce, not the expansion of empire, but connection. Intimate, direct, miraculous connection. We do not know if such connections are possible. The physics is ambiguous, the mathematics unresolved, the experimental evidence non-existent. But we are allowed to wonder. We are allowed to dream. And in our dreams, the wormhole remains open. A passage through the darkness, a bridge across the void, a reminder that distance is not always what it seems. So rest now, let your mind drift, not toward the singularity but toward the throat of a wormhole, that hypothetical tunnel through folded space-time. You do not need to cross it. You do not need to know where it leads. You only need to imagine it, to hold it in your mind as a possibility, a might be, a perhaps. The universe is vast and strange, and we have only begun to map its contours. There may be shortcuts we have not yet discovered. There may be passages we have not yet dreamed. And even if there are not, even if the distances between stars remain forever unbridgeable, the act of dreaming itself is a kind of travel. Your mind, tonight, has crossed light years. Your imagination has touched the edge of a wormhole's mouth. That is enough. That is more than enough. There is a ghost that haunts the black hole, and its name is information. Not information in the ordinary sense, not facts or figures, not dates and names, not the contents of books or the bits in a computer's memory. Information, in the language of physics, is something deeper and more elusive. It is the pattern of a thing, the arrangement of its atoms, the quantum state that distinguishes one particle from another, one history from another, one universe from another. Information is the difference that makes a difference. It is the signature of individuality in a cosmos that otherwise treats all electrons as identical, all protons as interchangeable, all fundamental particles as perfect, featureless copies of one another. And information, according to the laws of quantum mechanics, cannot be destroyed. It can be scrambled, hidden, transformed, encrypted, but never annihilated. The total amount of information in a closed system remains constant, as immutable as energy, as persistent as charge. This is not a suggestion or an approximation. It is a theorem proven and reproven, tested and confirmed, woven into the deepest fabric of our understanding of reality. Information is immortal. Then black holes arrived, and everything became complicated. Imagine, if you will, a book, not a digital file, not a cloud backup, but a physical book, paper and ink, binding and glue, the weight of it solid in your hands. This book contains a story, a history, a poem, a prayer. It contains information, carefully encoded in the arrangement of letters on pages, in the sequence of words, in the syntax and semantics of language. Now imagine throwing this book into a black hole. It crosses the event horizon. It falls toward the singularity. It is shredded by tidal forces, its atoms pulled apart, its nuclei dissolved, its quarks liberated. The paper and ink become plasma, become particles, become part of the black hole's mass. The book as a book ceases to exist. What happened to the information? The story, the poem, the prayer, where did it go? According to general relativity, it is gone forever. The black hole remembers only the book's mass, its spin, its charge. It does not remember the words. It does not remember the order of the letters. It does not remember the difference between a Shakespeare sonnet and a grocery list, between a love letter and a tax form. All that information, all that precious, hard-won difference, is erased as surely as words written in water. But quantum mechanics protests. Information cannot be destroyed, the equations insist. It must be preserved somewhere, somehow, in some form. Perhaps it is encoded on the event horizon itself, written in the quantum states of the particles that fell in, stored as holographic data on a two-dimensional surface. Perhaps it emerges in the Hawking radiation, slowly, patiently, over trillions of years, scrambled beyond recognition but still present, still recoverable in principle. Perhaps it passes through the singularity into another universe, another branch of reality, another page in the cosmic ledger. Perhaps, and this is the most radical possibility, perhaps we have misunderstood the nature of information entirely. This is the black hole information paradox, and it has tormented physicists for nearly 50 years. The paradox was first articulated in its modern form by Stephen Hawking himself, the same Hawking who gave us Hawking radiation and spaghettification and the strange, playful terminology of black hole physics. In 1976, 2 years after he proposed that black holes emit radiation, Hawking published a paper arguing that this radiation carries no information. It is thermal, random, featureless, the hiss of static, not the signal of a voice. The black hole, in evaporating, simply returns energy to the universe. The information it contained is lost forever. This was not a casual claim. Hawking was not being provocative for its own sake. He was following the mathematics, tracing the implications of general relativity and quantum field theory to their logical conclusions. And those conclusions pointed to a devastating possibility: that the laws of physics, as we had formulated them, were incomplete. That somewhere in the marriage of gravity and quantum mechanics, a fundamental principle had to give way. Either information was not conserved, or black holes were not truly black, or our understanding of space-time was fundamentally flawed. The debate raged for decades. Hawking held his position stubbornly, defending the irreversibility of black hole evaporation against a growing chorus of critics. In 1997, he made a famous bet with the physicist John Preskill, wagering that information is indeed lost in black holes and that the laws of quantum mechanics must therefore be modified. It was, by all accounts, a gentleman's bet, an encyclopedia to be awarded to the winner, but it symbolized the depth of the disagreement. Two brilliant physicists, both committed to the pursuit of truth, staring into the same abyss and seeing different shadows. Then, in 2004, Hawking conceded. He had found a new calculation, a new approach, a new way of thinking about the problem. The event horizon, he now believed, is not the absolute boundary he had once imagined. Quantum effects cause it to fluctuate, to ripple, to become something more porous and less final. Information can leak out, encoded in the Hawking radiation, preserved through the black hole's long evaporation. He announced his revised conclusion at a conference in Dublin, paying off his bet with a baseball encyclopedia. The physics community exhaled. The paradox, it seemed, was resolved. But was it? Hawking's concession was a shift in opinion, not a derivation from first principles. He had offered a plausibility argument, not a proof. The precise mechanism by which information escapes the black hole remains elusive, buried in the mathematics of quantum gravity, waiting for a theory we do not yet possess. The information paradox is not solved. It is perhaps more urgent than ever. Today, most physicists believe that information is preserved. They believe this not because they have seen the evidence. We cannot, after all, observe a black hole's evaporation. The timescales are far too long, but because the alternative is worse. To abandon information conservation is to abandon quantum mechanics itself, to tear out one of the central pillars of modern physics and hope the roof does not collapse. Better to assume that the information is preserved, somehow, somewhere, and spend our careers searching for the how and the where. This search has led to some of the most profound and speculative ideas in contemporary physics. The holographic principle, first proposed by Gerard T. Hooft and Leonard Susskind, suggests that all the information inside a region of space can be encoded on its boundary, that the three-dimensional interior of a black hole is, in some deep sense, a projection of a two-dimensional surface at the event horizon. This is not metaphor. It is a claim about the fundamental nature of reality, a claim that space itself may be emergent, derived from more primitive quantum information. If the holographic principle is correct, then the book you threw into the black hole is not lost. Its information is written on the horizon, stored in the quantum states of particles that have not yet fallen, preserved until the final instant of evaporation and then released, photon by photon, back into the cosmos. The anti-de Sitter/conformal field theory correspondence, or ADS/CFT, gives this intuition mathematical teeth. It maps a gravitational universe, a universe containing black holes, singularities, curved space-time, onto a lower dimensional quantum field theory without gravity. The two descriptions are equivalent, dual, two languages for the same underlying reality. What looks like information loss in one language looks like information preservation in the other. The paradox, from this perspective, is not a contradiction but a translation error. We were asking the question in the wrong dialect. And yet, even with these powerful tools, the information paradox retains its sting. We do not know how information escapes the black hole without violating causality, without sending signals faster than light, without breaking the very space-time geometry that defines the event horizon. We do not know whether the information emerges gradually, throughout the evaporation, or in a final, explosive burst when the black hole shrinks to Planck size. We do not know whether the information is scrambled beyond any hope of recovery, or whether it remains, in principle, perfectly reconstructible. We do not know. We are still asking. So the ghost remains. Information, that immortal, intangible essence, haunts the event horizon, trapped between the certainties of quantum mechanics and the absolutes of general relativity. It is the black hole's deepest secret, the question it poses to every physicist who dares to study it. And like all ghosts, it will not rest until it is understood. Rest now and consider the information that constitutes you. Your memories, your dreams, your sense of self. These are patterns, arrangements, differences that make a difference. They are encoded in the connections between your neurons, in the quantum states of the molecules that flow through your bloodstream, in the particular configuration of atoms that has, since your birth, maintained the fragile miracle of your existence. This information is not eternal. Your neurons will eventually fall silent. Your molecules will disperse. Your atoms will return to the great cosmic inventory, to be recycled into new stars, new planets, new life. But the laws of quantum mechanics promise that your information is not destroyed. It is transformed, scrambled, woven into the fabric of reality in ways we cannot yet trace. You are not lost. You are not erased. You are, like all information, immortal. And somewhere, in the distant future, when the last black hole has evaporated and the last photon has faded to silence, the information that was you will still exist, patient, preserved, waiting for a universe that can read it again. There is a place in the night sky, near the tail of the constellation Sagittarius, where the stars cluster thickly and the Milky Way arches across the darkness like a bridge of powdered glass. To the naked eye, it is unremarkable, just another patch of the galactic band, luminous with the combined light of millions of distant suns. But if you could see the sky in radio waves, if your eyes were sensitive to the long, slow oscillations of electromagnetic radiation that pass through clouds and dust and the empty spaces between stars, you would behold something else entirely. At the center of that unremarkable patch, there is a glow. Not a star, not a nebula, not any ordinary celestial object. It is a glow that marks the presence of something massive, something dense, something that has waited, patient and still, for more than 4 billion years at the very heart of our galaxy. Its name is Sagittarius A star, pronounced Sagittarius A star. The asterisk a quiet acknowledgement that this is no ordinary point of light. It is a radio source, first detected in the 1970s, and for decades astronomers debated its nature. Was it a cluster of dead stars? A dense accumulation of neutron remnants? Some exotic object we had not yet imagined? The debate could not be settled by direct observation. Sagittarius A asterisk was hidden behind veils of interstellar dust, invisible to optical telescopes, accessible only to the longer wavelengths that could pierce the galactic fog. But evidence accumulated, slowly, patiently, like sediment settling at the bottom of a still lake. The breakthrough came not from looking at Sagittarius A asterisk itself, but from watching the stars that orbited it. For more than 20 years, two teams of astronomers, one led by Reinhard Genzel, the other by Andrea Ghez, pointed their telescopes at the galactic center year after year, decade after decade, tracking the motion of individual stars as they traced their elliptical paths through the darkness. They watched one star, designated S2, complete a full orbit in just 16 years, a frenetic pace compared to our sun's leisurely 200 million-year circuit of the galaxy. They calculated the mass required to hold S2 in such a tight, swift embrace. The number they arrived at was staggering. Approximately 4 million times the mass of our Sun. And all of that mass was contained within a region no larger than our solar system. There is only one kind of object that can pack 4 million suns into such a small volume. There is only one kind of object that can be simultaneously invisible and inescapable. Sagittarius A*, the quiet glow at the center of the radio maps, is a supermassive black hole. It is our black hole. It has been there waiting since before Earth was born, since before the Sun ignited its nuclear fire, since before the spiral arms of the Milky Way coalesced from the primordial hydrogen fog of the young universe. It has watched generations of stars form and fade, has seen comets and planets and perhaps entire civilizations rise and fall in the galactic suburbs far from its patient gaze. It has not *moved. It has not changed. It has simply been a fixed point in the turning wheel of the galaxy. But Sagittarius A* is not the only supermassive black hole we have studied. In 2019, an international collaboration of more than 200 scientists unveiled something unprecedented. The first direct image of a black hole's shadow. The black hole in question, designated M87, sits at the center of the Virgo A galaxy, 55 million light-years from Earth. It is far larger than Sagittarius A, 6.5 billion solar masses, more than 1,000 times heavier than our own galactic center. Its event horizon is vast enough to swallow our entire solar system several times over. And yet, despite its enormous distance, despite the 55 million years it takes its light to reach us, the Event Horizon Telescope managed to capture its silhouette. The image, when it was released, was not what many expected. It was not a sharp photograph, not a clear portrait of a black hole in sharp relief against the starry background. It was blurry, impressionistic, a glowing orange ring surrounding a dark center that was not quite black and not quite empty. The ring is not the black hole itself. The ring is the photon sphere, that region where light orbits the singularity in unstable, eternal circles. The darkness at the center is not the event horizon but its shadow, the absence of light against the glow of hot gas spiraling inward. The image is not a photograph in the ordinary sense. It is a reconstruction, a translation, a composite of petabytes of data gathered by 8 radio telescopes across 4 continents, synchronized with atomic clocks and correlated by supercomputers. It is the product of years of patient observation and even more patient calculation. And it is, by any reasonable definition, a miracle. 2 years later, in 2022, the same collaboration released a second image. This time, the subject was Sagittarius A* itself, our own black hole, the quiet heart of the Milky Way. The image was similar to M87, a luminous ring surrounding a dark shadow, the signature of extreme gravity bending light around an invisible center. But there were differences. Sagittarius A is 1,000 times smaller than M87, and its event horizon subtends an angle in the sky comparable to a donut on the surface of the moon. Capturing its image required even greater precision, even more careful calibration, even more painstaking reconstruction. And because Sagittarius A is so small, its accretion disk flickers and changes on timescales of minutes. Imagine trying to photograph a candle flame that dances and shifts with every breath of air. The team succeeded not by taking a single image, but by averaging thousands of snapshots, smoothing the variability into a stable, representative portrait. The result is a kind of self-portrait. We, the inhabitants of a small planet orbiting an ordinary star in the outer reaches of the Milky Way, have looked toward the center of our galaxy and seen the shadow of the darkness that dwells there. We have measured its mass, traced its spin, mapped its influence on the stars that circle it. We have confirmed, beyond any reasonable doubt, that Einstein's equations, written down more than a century ago in the relative calm of a Berlin apartment, hold true even in the most extreme gravitational environment the universe can produce. And we have done all of this not with a single heroic observation, but with decades of patient work, thousands of nights of telescope time, the labor of generations of scientists who devoted their careers to the pursuit of an invisible quarry. There is a humility in this achievement, a quiet recognition that understanding does not arrive in a flash of inspiration but accumulates slowly, like sediment, like starlight, like the gradual revelation of a black hole's shadow against the glow of its accretion disk. We did not conquer Sagittarius A star. We did not tame it or capture it or reduce it to a tidy set of equations. We simply looked at it, patiently, persistently, until it yielded some small fragment of its mystery. And in that looking, we learned something about ourselves, that we are the kind of creatures who spend decades chasing shadows, who dedicate our lives to questions that will not be answered in our lifetimes, who find meaning not in final victories but in the slow, steady advance of understanding. So rest now and consider that darkness at the center of our galaxy. It is not a threat. It is not a predator waiting to consume us. It is simply there, as it has been for billions of years, a fixed point in the turning wheel of the Milky Way. Its gravity holds the inner galaxy together, shapes the orbits of stars, influences the flow of gas and dust that will one day form new suns and new worlds. It is not our enemy. It is not our friend. It is not anything we can easily name. It is simply Sagittarius A asterisk, the quiet heart of our galactic home, the shadow we have finally learned to see. For most of its existence, the black hole at the center of our galaxy has been quiet, not silent. There are always wisps of gas drifting too close, the occasional star venturing too near the event horizon and paying the ultimate price for its recklessness. But quiet, in the way a dormant volcano is quiet. It does not blaze across the electromagnetic spectrum. It does not outshine the billions of stars that surround it. It waits, patient and still, its accretion disk a faint whisper of plasma rather than a roaring cataract of X-rays. Sagittarius A asterisk is, by supermassive black hole standards, a sleeper. But not all black holes sleep. Not all wait in patient stillness at the hearts of their galaxies. Some feed, some feast, some draw matter inward with such furious appetite that the energy released by their accretion disks outshines every star in the host galaxy combined. These are the quasars, the active galactic nuclei, the most luminous persistent objects in the universe. And they are not curiosities or anomalies. They are, in a very real sense, the architects of galaxies. To understand why, we must expand our view. A black hole, even a supermassive one, is tiny compared to the galaxy that hosts it. Sagittarius A asterisk weighs 4 million suns, but the Milky Way weighs more than 1 trillion. The black hole is less than 1/10,000th of 1% of its host's mass. A speck, a mote, a negligible fraction of the galactic whole. And yet this speck shapes the galaxy around it with an influence far out of proportion to its size. It is the still point at the center of the turning wheel, the quiet heart around which everything else must orient itself. The mechanism of this influence is feedback. As matter spirals into a supermassive black hole, it releases not only radiation but also outflows. Jets of plasma accelerated to nearly the speed of light, winds of hot gas driven by the fury of the accretion disk, magnetic fields twisted and amplified by the black hole's spin. These outflows travel outward, far beyond the event horizon, far beyond the accretion disk, far beyond the sphere of stars that immediately surrounds the galactic center. They push against the interstellar medium. They heat the gas that would otherwise cool and collapse into new stars. They regulate with exquisite and brutal efficiency the rate at which the galaxy can form its next generation of suns. This is the paradox of the supermassive black hole. It is simultaneously a destroyer and a creator. Its jets can strip gas from the galaxy, quenching star formation and rendering the host a red and dead desert of ancient, fading suns. But those same jets can also compress gas, triggering collapses that birth new stars in dense clusters. Its winds can heat the interstellar medium to millions of degrees, preventing the slow gravitational settling that leads to star formation. But those winds can also carry heavy elements, carbon, oxygen, iron, far from the galactic center, seeding the outer reaches with the raw materials of planets and life. The black hole is not merely a passive sink at the bottom of a gravity well. It is an active participant in the life of its galaxy, sculpting and shaping the very environment that feeds it. Nowhere is this more evident than in quasars. The word is a contraction of quasi-stellar radio source, a clumsy label that betrays the confusion of astronomers who first detected these objects in the 1950s and 60s. They appeared as points of light, indistinguishable from stars in photographic plates, but their spectra revealed something impossible. Their spectral lines were shifted so far toward the red that they could only be explained by enormous distances, billions of light years, far beyond the edge of our own galaxy. And yet they were visible, bright enough to be seen across most of the observable universe. An ordinary star, no matter how luminous, could not shine so brilliantly from such immense distances. These objects, whatever they were, must be something else entirely. We know now that quasars are not stars but galaxies whose central supermassive black holes are in the midst of a feeding frenzy. The accretion disk around such a black hole is not a faint whisper but a roaring cataract, matter spiraling inward so rapidly and so densely that it glows across the entire electromagnetic spectrum. The energy released by a single quasar can exceed the output of 1 trillion suns. And that energy pouring outward from the galactic core shapes the destiny of the entire host galaxy. The relationship between a supermassive black hole and its galaxy is not one-sided. The galaxy feeds the black hole, funneling gas and stars toward the center, sustaining its luminous outburst. But the black hole, in turn, feeds back on the galaxy. Its radiation heats the surrounding gas. Its winds drive material outward. Its jets carve cavities in the intergalactic medium, bubbles of hot plasma that can extend for millions of light years. The two are coupled, bound together in a dance of consumption and regulation that spans cosmic epochs. We see evidence of this coupling in the remarkable correlation between a galaxy's central black hole and the properties of the galaxy itself. The mass of the black hole is proportional to the velocity dispersion of the stars in the galactic bulge. The faster the stars move, the more massive the black hole. This is not coincidence. It is not the result of independent formation processes. It is a signature of feedback, of coevolution, of the intimate and inescapable relationship between the darkness at the center and the light that surrounds it. And yet, even as we trace these connections, even as we map the influence of black holes across cosmic distances and galactic scales, we are left with a question that touches the deepest mysteries of structure formation. Which came first? Did the black hole grow large and then shape its galaxy? Or did the galaxy assemble and then funnel matter inward to feed its central beast? The answer, as with so many questions in astrophysics, is both and neither. The growth is concurrent, intertwined, a single process viewed from two perspectives. The black hole and the galaxy are not separate entities. They are a system, a unity, a single evolving organism whose components cannot be understood in isolation. This is the final lesson of the quasar, the active nucleus, the feeding supermassive black hole. Darkness is not the opposite of light. It is not the absence of creation. It is, in ways we are only beginning to understand, a participant in creation, a sculptor of galaxies, a regulator of star formation, a distributor of the heavy elements that make planets and life possible. The black hole at the center of a quasar is not a monster devouring its host. It is a heart pumping energy and matter through the galactic body. It is a forge transmuting the raw hydrogen of the early universe into the carbon and oxygen that will one day form the bones of living creatures. It is, in its own patient and terrible way, a creator. So rest now and consider the darkness at the center of distant galaxies. It is not a void. It is not an absence. It is an engine, a sculptor, a gardener tending the cosmic fields. Its jets carve channels through intergalactic space. Its winds scatter the seeds of future worlds. Its gravity holds galaxies together even as its radiation pushes them apart. And somewhere, in a quiet corner of an ordinary spiral galaxy, a small planet orbits a modest star, and on that planet, creatures have begun to understand the role of darkness in the story of their own existence. They have looked at the centers of distant galaxies and seen, in the brilliance of quasars, the signature of creation. They have looked at the heart of their own galaxy and seen, in the quiet shadow of Sagittarius A*, the patient hand of the sculptor at rest. We are those creatures. This is our understanding, and it grows slowly, patiently, with each generation of telescopes and each night of observation, like sediment settling at the bottom of a still lake, like starlight accumulating on a photographic plate, like the slow, steady accretion of matter onto the waiting mouth of a sleeping giant. We have, throughout this long and patient descent, treated the black hole as a destination, terminus, the end of the line for matter and light and information. But what if we have been looking at it backward? What if the singularity is not a wall but a doorway? What if the fall does not end in annihilation but in emergence, a birth, a beginning, a passage into some other realm of existence? These are not questions that can be answered by observation. No signal returns from beyond the event horizon. No traveler has come back to tell us what lies at the bottom of the gravity well. But the mathematics, that strange and flexible language, permits us to imagine. And so we imagine. The concept of the white hole emerges naturally from the equations of general relativity. It is the time-reverse twin of the black hole, not a sink but a source, not a point of infinite attraction but a point of infinite repulsion. Where a black hole swallows matter and light, a white hole spews them forth. Where a black hole's event horizon is a one-way door inward, a white hole's horizon is a one-way door outward. Nothing can enter a white hole, everything must leave. It is, in a sense, a black hole playing the film backward, the collapse reversed into expansion, the fall reversed into ascent, the final silence reversed into a primordial shout. Do white holes exist? Almost certainly not. They are solutions to Einstein's equations, yes, but they are unstable solutions, ephemeral as soap bubbles. Any matter that approached a white hole's horizon would perturb it, trigger a collapse, transform it into a black hole. White holes, if they ever formed, would not survive long enough to be observed. They are mathematical ghosts, relics of a symmetry that reality does not honor. And yet the idea persists, because the white hole offers us something the black hole cannot: hope. Hope that the journey does not end at the singularity. Hope that what falls in might someday come out. Hope that the darkness is not absolute but merely the shadow of a door. This hope takes many forms. Some theorists have proposed that black holes and white holes are connected, that the singularity is not a point of destruction but a tunnel, a throat, a bridge linking our universe to another. The matter that falls into a black hole does not accumulate at a point of infinite density. It passes through the singularity and emerges, somewhere else, sometime else, as a white hole's exhalation. The black hole's event horizon and the white hole's horizon are the two ends of a single passage through folded spacetime. This is the Einstein-Rosen bridge, the wormhole, the hypothetical shortcut through the fabric of reality. It is not traversable, not in any practical sense. The throat pinches shut before anything can cross. But the mathematics allows it. The possibility remains. Other theorists have pushed the idea further. Perhaps the singularity is not a bridge to another region of our universe, but a gateway to an entirely new cosmos. Perhaps each black hole contains within its event horizon the seed of a baby universe, a nascent space-time that buds from the parent cosmos, inflates, expands, and grows into a realm of its own. Our universe, in this picture, may itself be the interior of a black hole formed from the collapse of matter in some prior cosmos. The Big Bang was not the beginning of everything but the exhalation of a white hole, the moment when a singularity in another universe reversed its collapse and spewed forth the primordial fireball from which all we see and know and love eventually emerged. This is not physics, not yet. It is speculation, imagination, the play of equations in the space between established knowledge and untested hypothesis. But it is not arbitrary speculation. It is speculation constrained by mathematics, disciplined by the rigorous language of general relativity and quantum mechanics. It is the product of physicists who have spent their careers wrestling with Einstein's equations and have found, hidden within those elegant symbols, possibilities that Einstein himself may never have imagined. And then there is the most radical possibility of all, that black holes are not physical objects but information processors. That the universe, at its most fundamental level, is not made of particles and fields but of bits and qubits, of ones and zeros, of yes and no. That space-time itself is emergent, derived from the quantum entanglement of more primitive degrees of freedom. And that black holes, those extreme distortions of space-time, are the places where this underlying information-theoretic nature becomes manifest. This is the holographic principle, and it suggests a vision of black holes that is at once more abstract and more beautiful than the classical picture. In this vision, The three-dimensional interior of a black hole is a kind of illusion, a projection of information encoded on the two-dimensional surface of the event horizon. Everything that falls into the black hole is not destroyed but stored, its quantum states written on the horizon like data on a cosmic hard drive. The black hole's mass, its spin, its charge, these are not fundamental properties but thermodynamic averages, macroscopic manifestations of the microscopic information stored at the horizon. And when the black hole evaporates through Hawking radiation, that information is not lost but gradually released, encoded in the correlations between emitted particles, preserved across the black hole's lifetime and beyond. In this picture, the singularity is not a point of infinite density but a region where our description of spacetime breaks down. Not because spacetime becomes infinitely curved, but because spacetime itself ceases to be a useful concept. The singularity is not a place but a boundary, a place where the smooth geometry of general relativity gives way to the discrete, quantum information theoretic substrate from which geometry emerges. It is not the end of physics but the threshold of a deeper physics, a physics we have not yet learned to speak. This is the frontier where black hole research now stands. Not the frontier of observation. We will not, in any foreseeable future, send probes to the event horizon or recover signals from beyond it. But the frontier of theory, of mathematics, of the slow, patient work of reconciling Einstein's vision of curved spacetime with the quantum vision of particles and fields and information. The black hole is the laboratory where this reconciliation must occur, the crucible in which the next great theory of physics will be forged. And so the black hole, which began as a simple solution to Einstein's equations, has become something far more profound. It is not merely an object of study but a teacher. It teaches us about the life cycles of stars and the evolution of galaxies. It teaches us about the nature of time and the behavior of matter under extreme conditions. It teaches us about the limits of our knowledge and the humility we must cultivate when we approach those limits. And it teaches us, most of all, that the universe is stranger, richer, and more beautiful than we ever imagined. What lies inside a black hole? We do not know. Perhaps a singularity, a point of infinite density where the laws of physics break down. Perhaps a bridge, a wormhole, a passage to another universe. Perhaps a fuzzball of quantum strings, each one vibrating in a different dimension. Perhaps a holographic projection of information encoded on a distant surface. Perhaps something we have not yet imagined, something that will require not just a new theory but a new way of thinking about what a theory is. We do not know, but we are learning. Slowly, patiently, one equation at a time, one observation at a time, one generation of scientists at a time. The black hole keeps its secrets, but it does not keep them forever. It yields them grudgingly to those who ask the right questions in the right language. And we, the askers, the seekers, the ones who look up at the night sky and wonder, we are learning to speak that language. So rest now and consider the possibility that the darkness is not an ending. Consider that every black hole may be a doorway, every singularity a birth, every fall an ascent. Consider that the universe we inhabit may itself be the interior of a black hole, the exhalation of a white hole, the projection of information encoded on a distant horizon. These are not certainties. They are not even probabilities. They are possibilities, dreams, the play of imagination in the space between knowledge and ignorance. But they are beautiful possibilities, and sometimes beauty is enough. There is an image that haunts our collective imagination, cultivated by decades of science fiction and cinematic spectacle. It is the image of the black hole as a cosmic vacuum cleaner, a roving, ravenous monster that prowls the galaxy, sweeping up planets and stars in its insatiable hunger. In this image, the black hole is active, aggressive, a predator with an appetite that can never be satisfied. It chases down fleeing starships. It drags helpless worlds into its gaping maw. It is, in every sense that matters, a villain. This image is wrong. Not subtly wrong, not approximately wrong, but fundamentally, categorically, almost completely wrong. And yet it persists, not because we are ignorant or careless, but because it satisfies a deep narrative need. We understand villains. We understand hunters and prey, eaters and eaten. What we struggle to understand is something that simply waits, patient, passive, utterly indifferent to the worlds that circle it in perfect safety. The truth about black holes is quieter than fiction. It is also, in its own way, more beautiful. Let us begin with the most persistent myth, that black holes go around sucking things in. They do not. A black hole's gravity at a given distance is exactly the same as the gravity of any other object with the same mass. If the sun were suddenly replaced by a black hole of one solar mass, Earth would continue its orbit unchanged. There would be no dramatic death spiral, no inexorable plunge into darkness. The planet would freeze, certainly, deprived of its star's warmth. But it would not fall in. The black hole, like the sun before it, would hold Earth in its gentle gravitational embrace, asking nothing more than patience and distance. This is the first and greatest misunderstanding we must release. A black hole is not a hunter. It does not reach out to snatch passing stars or drag reluctant planets from their orbits. It simply sits, curving the space-time around it, waiting for matter to venture too close. And too close is a very small region indeed. For a stellar mass black hole, the event horizon is only a few kilometers across. For Sagittarius A*, our galactic center's supermassive giant, the horizon spans about 12 million kilometers. Wide enough to swallow the inner solar system, yes, but tiny compared to the galaxy that surrounds it. The space between stars is vast, empty, patient. The chance of any given star approaching within that radius is infinitesimally small. Most black holes will spend eternity alone, their horizons untouched, their silence unbroken. The second myth concerns the appearance of black holes. In film and television, they are often depicted as swirling vortices, tunnel-like openings in the fabric of space, surrounded by concentric rings of captured light. This image, unlike the vacuum cleaner myth, has some basis in science. The accretion disk of a feeding black hole does indeed swirl. The photon sphere does indeed bend light into rings. But these features are not the black hole itself. They are the environment around it, the decoration on the wall, not the wall itself. The black hole, strictly speaking, is invisible. It emits no light, reflects no light, bends light but does not generate it. What we see, in the famous Event Horizon Telescope images, in simulations, in the artistic renderings that accompany scientific papers, is not the black hole but its shadow, its silhouette, the absence of light against a brighter background. The black hole itself remains hidden, patient, unrevealed. A third myth concerns the experience of falling into a black hole. In popular culture, this is almost always portrayed as instantaneous destruction. A flash of light, a scream cut short, the traveler erased at the moment of crossing. The reality, as we have explored, is more complex and more merciful. For a supermassive black hole, the tidal forces at the event horizon are negligible. You would cross it without sensation, without awareness, without any sign that you had passed the point of no return. You would then have hours, perhaps days, of further fall before the tidal forces grew strong enough to spaghettify you. And even then, the process would be gradual, a slow elongation rather than a sudden tearing. The black hole does not kill you instantly. It invites you, gently, into its long and patient embrace. There is also the persistent myth that black holes are portals, gateways to other dimensions, other times, other universes. This idea, like so many others, has its roots in legitimate physics. The mathematics of general relativity does permit solutions that connect black holes to white holes, that bridge distant regions of space-time, that tunnel through to hypothetical alternate realities. But these solutions are, as far as we can tell, mathematical curiosities rather than physical descriptions. Real black holes, born from collapsing stars and fed by accretion disks, contain singularities that are not passages but endpoints. The dream of the wormhole is beautiful, compelling, almost irresistible, but it remains a dream. We have no evidence that such passages exist. We have no plausible mechanism for creating or stabilizing them. We have only the hope that the universe is kinder than the equations suggest. A fifth myth, more subtle than the others, concerns the role of black holes in the cosmos. We tend to think of them as destroyers, annihilators, erasers of matter and information. And in a sense, they are. Anything that crosses the event horizon is lost to our universe, unmade at the singularity, reduced to its constituent mass and spin and charge. But this is not the whole story. Black holes are also creators. Their jets seed galaxies with heavy elements. Their gravity shapes the orbits of stars. Their accretion disks outshine entire galaxies, visible across billions of light years. They are not merely endings but transformations, not merely deaths but rebirths. The universe does not waste its resources. Even its darkest regions serve a purpose we are only beginning to understand. And finally, there is the myth of fear. We are taught, implicitly and explicitly, that black holes are terrifying, objects of dread, symbols of cosmic indifference, reminders of our own insignificance. But this fear, like so many of our fears, is a product of misunderstanding. The black hole is not malevolent. It is not a punishment or a threat. It is simply a phenomenon, as natural as a waterfall, as lawful as the orbit of a planet, as beautiful as the spiral of a galaxy. It does not hate us. It does not love us. It does not know we exist. And in that ignorance, there is not terror but peace. The universe is not arrayed against us. It simply is. So rest now and release these myths. Let go of the image of the black hole as a cosmic predator, a hungry mouth, a one-way ticket to annihilation. Replace it gently with something else. Replace it with the image of a well, deep and still, at the bottom of which lies a mystery we have not yet solved. Replace it with the image of a patient giant, waiting at the center of galaxies, its horizon invisible, its shadow cast against the glow of infalling matter. Replace it with the image of a teacher, offering lessons about gravity and time and the limits of human knowledge. Replace fear with wonder. Replace dread with curiosity. Replace the monster with the mystery. The black hole is not our enemy. It is not our friend. It is not anything we can easily name. It is simply there, as it has been for billions of years, waiting in the darkness for the questions we have only begun to ask. And in that waiting, there is not threat but invitation. An invitation to learn, to wonder, to rest in the quiet certainty that the universe still holds secrets we have not yet discovered. That is not a cause for fear. That is a cause for gratitude. We have traveled far together, you and I. We have traced the life cycles of stars and watched their cores collapse into darkness. We have approached the event horizon and hesitated at its threshold. We have followed the fall of matter and light and information toward the singularity, that point of infinite density where the equations stutter and fall silent. We have wondered about wormholes and white holes, about the fate of information and the nature of time. We have seen the shadow of our own galactic center and the quasar glare of distant supermassive giants. And now, at the end of this long and patient descent, we must ask ourselves, what remains unknown? The answer, it turns out, is almost everything. Not in the sense of utter ignorance. We are not lost, not groping blindly in the darkness. We have mapped the contours of black hole physics with remarkable precision. We understand their formation, their classification, their basic structure. We have detected their mergers across billions of light years. We have imaged their shadows. We have measured their masses and spins. We have confirmed, again and again, that Einstein's equations describe their gravitational influence with exquisite accuracy. In just over a century, we have transformed black holes from mathematical curiosities into observable, measurable, comprehensible objects of scientific study. And yet the core remains hidden. The singularity, that dimensionless point of infinite density, is not merely unknown but unknowable, at least within the framework of our current theories. It is the place where general relativity collides with quantum mechanics, and neither theory is willing to surrender. To understand what happens at the singularity, we need a new language, a new mathematics, a new way of thinking about the fundamental nature of reality. We need a theory of quantum gravity. And despite decades of effort by the brightest minds in physics, we do not yet have one. This is not failure. It is not a sign that we have reached the limits of human intelligence or that the universe has locked its secrets away from us forever. It is simply the frontier, the place where our current maps end and the wilderness begins. Every generation of scientists has faced such frontiers. For Newton, it was the nature of light and the cause of gravity. For Einstein, it was the quantum behavior of atoms and the structure of the nucleus. For us, it is the singularity. And like our predecessors, we are doing what explorers have always done when they reach the edge of the known world. We are building better ships. The next generation of gravitational wave observatories is already on the drawing boards. LISA, the Laser Interferometer Space Antenna, will launch in the 2030s, a constellation of 3 spacecraft separated by millions of kilometers, linked by laser beams, sensitive to the slow, deep ripples of supermassive black hole mergers. Where LIGO hears the chirp of stellar mass collisions, LISA will hear the basso profundo of galactic centers dancing their final waltz across cosmic time. It will extend our hearing to frequencies that are inaccessible from Earth, frequencies that carry information from the early universe, from the first generation of black holes, from the dawn of structure itself. The Event Horizon Telescope, which gave us our first images of M87* and Sagittarius A*, is expanding. New telescopes are joining the array, filling in the gaps in our virtual aperture, sharpening our view of the shadows at the centers of galaxies. Future observatories, the Next Generation Very Large Array, the Square Kilometer Array, the Black Hole Explorer mission, will image black holes with even greater resolution and sensitivity. They will map the magnetic fields that thread accretion disks. They will trace the orbits of stars and gas clouds closer to the event horizon than ever before. They will watch, in real time, as matter spirals toward its final destination. And beyond these, still on the horizon of possibility, are instruments we have not yet built and techniques we have not yet invented. Gravitational wave detectors that can probe the Planck scale. Telescopes that can image the quantum structure of spacetime itself. Observatories that can test, with ever-increasing precision, the predictions of general relativity in the most extreme environments the universe can produce. We do not know what these instruments will find. We do not know whether they will confirm our theories or overturn them. We do not know whether the singularity will yield its secrets to our questioning or remain forever beyond our reach. But we know that we will keep asking. We know that we will keep building. We know that we will keep pushing generation after generation toward the edge of the unknown. This is the great and quiet drama of science. Not the eureka moments, not the flashbulb discoveries, not the Nobel Prizes and the headlines. Those are the peaks, visible and celebrated. But the work of science happens in the valleys, in the patient accumulation of data, the slow refinement of theories, the long, steady march of understanding across decades and centuries. It happens in the minds of graduate students wrestling with equations at 3 in the morning. It happens in the control rooms of telescopes, where astronomers wait through cold desert nights for the photons to accumulate. It happens in the collaborations that span continents and generations, the handing down of questions from mentor to student, the inheritance of curiosity that connects us to our intellectual ancestors and will connect our intellectual descendants to us. We are part of that inheritance. Every question we ask, every mystery we contemplate, every wonder we feel is a thread in the vast tapestry of human inquiry. The ancient Greeks wondered about the nature of the cosmos and called the void between stars kenos, emptiness. Medieval astronomers traced the motions of planets and called the unchanging heavens quintessence. Newton imagined light as particles and gravity as a force acting at a distance. Einstein imagined light as waves and gravity as geometry. And we, standing on their shoulders, imagine black holes and singularities, wormholes and white holes, holographic principles and quantum foam. Our descendants will imagine things we cannot conceive. They will solve problems we cannot solve and answer questions we cannot ask. But they will inherit from us the tools we built and the questions we left behind. They will inherit the frontier. So what remains unknown? Almost everything. The singularity, the information paradox, the nature of quantum gravity, the origin of supermassive black holes, the fate of matter that crosses the event horizon, the possibility of wormholes and white holes and baby universes, the role of black holes in the evolution of galaxies and the large-scale structure of the cosmos, the connection between black hole thermodynamics and the ultimate fate of the universe. These are not gaps in our knowledge but invitations to future generations of scientists, future generations of telescopes, future generations of dreamers who will look up at the night sky and wonder, as we have wondered, as our ancestors wondered, as our descendants will wonder. The black hole keeps its secrets, But it does not keep them out of malice or mischief. It keeps them because the universe is vast and our lives are short, because understanding accumulates slowly and patience is the price of wisdom, because the questions are always larger than the answers and the mystery is always deeper than the revelation. The black hole is not a locked door but an open horizon. It is not the end of our journey but the beginning of the next journey, and the next and the next. We will not reach the end. There is no end. There is only the asking, the seeking, the slow and patient accumulation of understanding across the generations. And that is not failure. That is not tragedy. That is the great and quiet triumph of the human spirit. That we keep asking, keep seeking, keep pushing toward the edge of the unknown. Not because we expect to arrive, but because the journey itself is the destination. So rest now. You have traveled far tonight, from the birth of stars to the death of singularities, from the edge of the event horizon to the heart of the galactic center, from the first glimmer of gravitational waves to the final whisper of Hawking radiation. You have carried with you the weight of questions that have no answers and the lightness of wonder that needs no resolution. You have rested in the darkness and found not fear but peace. And now, at the end of this long and patient descent, it is time to return. The voice fades now, as all voices must. Not abruptly, not with a sudden silence that startles, but slowly, gently, like the last notes of a lullaby drifting into the spaces between sleep and waking. The black hole recedes, its shadow shrinking to a point, its gravity loosening its gentle hold on your attention. The accretion disk dims, the photon sphere fades, the event horizon, that invisible boundary between light and darkness, becomes a memory, a thought, a dream you are not sure you dreamed. You are here now, in your bed, your room, your quiet space. The blanket still holds its familiar weight across your chest. Your breath still rises and falls in its ancient rhythm. Your heartbeat, that steady drummer, keeps time with the turning earth. You have not fallen. You have not dissolved. You have not crossed any horizon or approached any singularity. You have simply listened, and in listening traveled farther than any astronaut could ever hope to go. The universe outside continues its patient turning. Stars burn and fade. Galaxies spiral and merge. Black holes wait, silent and still, at the centers of their cosmic webs. None of this depends on you. None of this requires your attention or your understanding. The cosmos does not need witnesses to be beautiful. But you are a witness nonetheless, one small consciousness on one small planet, in one small corner of an immense and ancient universe. You have looked into the darkness and seen not emptiness but wonder. You have asked questions that have no answers and found peace in the asking. Let that peace settle now, slowly, like sediment at the bottom of a still lake. Let the weight of the day dissolve. Let the thoughts of black holes and singularities drift into the background, not forgotten but transformed. No longer puzzles to solve but mysteries to rest in. You have done enough tonight. You have wondered enough. You have traveled enough. It is time to sleep. Wherever you are, whatever time the clock shows, whatever worries await you in the morning, know this: you are held by gravity, that patient hand that keeps you close to the earth, held by the atmosphere, that thin membrane of breathable air that separates you from the void. Held by the quiet certainty that the universe, for all its vastness and strangeness, is not indifferent to the creatures it has produced. It has given us stars to guide us, darkness to rest in, and questions to keep us company through the long night. Close your eyes now. Soften your gaze. Let the world slow down, not to a stop but to a gentle drift, like the fall of an astronaut toward a distant horizon. You are not falling. You are resting. You are not crossing any boundary. You are simply here, in this moment, in this breath, in this quiet space between waking and sleep. The black hole waits, patient and still, at the center of its galaxy. It will wait forever, but you have waited long enough. Sleep now. Dream of light and darkness, of gravity and grace, of the vast and beautiful universe that holds you in its invisible embrace. And when you wake, the sun will rise, the stars will fade, the questions will still be there, waiting for your return. But tonight you have earned your rest. Sweet dreams.